On a monitor in a quiet observatory archive, a star does something almost too small to notice. Its light falls by less than 1%, not suddenly and not with any visible drama, but in a shallow curve that repeats after a fixed number of days. To the eye, the star is only a point. To the camera, it is a cluster of pixels. To the software, it is a sequence of measurements, each one corrected for noise, scattered light, detector behavior, and the slow drift of the spacecraft. But when the dots are folded together, when one orbit is placed on top of another and another, a pattern begins to appear. Something is crossing that star. Something with a size, an orbit, a year of its own, and a shadow so small that it could vanish inside an error bar if the instruments were not patient enough to wait. This is how many alien worlds first enter human knowledge. Not as landscapes, not as oceans, not as continents under unfamiliar skies. They appear as missing light, as a stellar wobble, as a spectrum with one feature slightly deeper than another, as a planet that has never been seen directly, but has still left a measurable mark on the star it orbits. The discovery is not like finding a new island on a map. It is more like listening to a room through a wall and slowly realizing that someone is moving inside it. The evidence comes indirectly at first, and every conclusion has to be earned. A planet may be present. Its radius may be inferred. Its mass may be estimated. Its atmosphere may leave a trace. But between the trace and the world itself there is still distance, and that distance is measured in light years. At the beginning of the modern search, the word exoplanet sounded almost speculative, even though physics allowed no reason to think the sun should be unique. Stars form from collapsing clouds of gas and dust, and around young stars, leftover material naturally settles into rotating disks where grains collide, stick, grow, shatter, and grow again. In such disks, planets should be common. The logic was strong. The observations were not yet enough. For much of the 20th century, other planetary systems were expected, but unseen, suggested by theory and by the structure of our own solar system, but not confirmed around ordinary stars. Then, the measurements became precise enough to reveal that the galaxy had been full of planets all along. The first confirmed planets outside the solar system were not found around a star like the Sun. They were found around a pulsar, a dead stellar remnant spinning with astonishing regularity after a supernova had destroyed its original star. The system was strange, difficult to imagine as a birthplace for life, and not at all the comfortable planetary family astronomers had hoped to find first. But it mattered, because it proved that planets could exist beyond the sun, and that nature could build them in circumstances no one would have chosen as the obvious place to begin. A few years later, in 1995, the discovery of 51 Pegasi b changed the field again. This was a planet orbiting a sun-like star, but it was not like Jupiter where Jupiter should have been. It was a gas giant moving so close to its star that its year lasted only a few days. Hot Jupiters were not expected to be the first familiar answer. They were enormous planets in tight orbits, heated intensely by stars they nearly grazed, and their existence forced astronomers to reconsider how planetary systems evolve. A giant planet could not easily form where some of these worlds were found, because the region near the star would have been too hot for the icy building materials that help form massive cores. The evidence suggested migration. Planets could form farther out, then move inward through interactions with the disk or with other planets. Planetary systems were not clockwork arrangements frozen at birth. They were histories of motion, scattering, collisions, survival, and sometimes loss. By the time the catalogs grew, the solar system no longer looked like the standard arrangement from which all other systems were mild variations. It became one example among many. There were super-Earths, larger than Earth and smaller than Neptune, common in the galaxy but absent from our own planetary family. There were mini-Neptunes, dense worlds wrapped in thick envelopes of gas. There were planets orbiting two stars, planets around red dwarfs, planets in resonant chains, planets with years shorter than a day, and cold giants far from their suns. Some worlds were so close to their stars that rock itself may rain or vaporize. Others were so distant that their stars would look like bright points, not suns. None of this made the search for life simpler. It made it wider. The official count of confirmed exoplanets has now moved beyond 6,000, and thousands of candidates still wait for confirmation. That number is not just a tally, it is a measure of how quickly the unknown can change when instruments improve. The galaxy did not become richer in planets. During the last 30 years, human evidence became richer. Spacecraft watched star fields for tiny dimmings. Spectrographs measured stellar motions at speeds comparable to a walking person. Algorithms searched through archived light curves for repeated dips that older surveys had missed. Every confirmed planet is an answer to one question and a beginning for many others. How large it is, how massive it is, what kind of star it orbits, whether it has an atmosphere, whether that atmosphere is stable, and whether its surface or interior could ever support chemistry complex enough to matter. If these long journeys through distant worlds are what bring you here, subscribing keeps the next quiet search within reach. The question beneath all of this is not only whether planets exist. That part is no longer in doubt. The deeper question is what kinds of planets exist, how often they keep water, how often they hold on to air, and whether life is a rare accident of Earth or a possible outcome of ordinary chemistry under ordinary stars. Alien life, if it exists, may not announce itself with a signal or a city or a spacecraft. It may be a faint imbalance in an atmosphere, a chemical pairing that should not persist without renewal, a pigment edge in reflected light, a seasonal change, a gas in the wrong quantity, or a pattern that only becomes convincing after years of observation. The search for life is therefore not one search. It is many searches layered together. A planet is not habitable just because it is the right size. And it is not alive just because it is in the habitable zone. The habitable zone is a useful idea, but it is only a starting point, the region around a star where liquid water could exist on a planet's surface under the right atmospheric conditions. Venus lies near the inner edge of our Sun's habitable zone and is a furnace under clouds of sulfuric acid. Mars lies near the outer edge and is cold, dry, and thin-aired at the surface. Earth is habitable not because its orbit alone makes it so, but because its orbit works together with its mass, atmosphere, oceans, geology, magnetic environment, and history. Habitability is not a circle drawn around a star. It is a planet's whole biography. A star's light can build a climate, but it can also strip one away. Red dwarfs, the most common stars in the Milky Way, are small, cool, and long-lived. Their habitable zones sit close in, which makes planets easier to find because they transit more often and tug their stars more strongly. But closeness has consequences. A planet near a red dwarf may become tidally locked, with one hemisphere always facing the star and the other turned toward permanent night. It may be exposed to flares and high-energy radiation, especially when the star is young and restless. Models show that some tidally locked worlds could still circulate heat with a thick enough atmosphere or ocean. But whether a specific planet managed to keep such conditions is not something a light curve alone can reveal. Across the galaxy, most planets are beyond reach in a very practical sense. No probe is on the way. No telescope can resolve continents on their surfaces. Even the nearest star systems remain separated from us by distances that make human engineering feel young. Proxima Centauri b, if it has a surface, receives light from a red dwarf more than 4 light-years away. TRAPPIST-1, with its 7 roughly Earth-sized planets, lies about 40 light-years away. K2-18b is roughly 120 light-years away. These are close systems by galactic standards, but their light still needs years or decades or more than a century to cross the darkness and arrive at our instruments. We study them not by visiting, but by catching the small portions of their starlight that carry information home. The transit method is simple in concept and difficult in practice. If a planet crosses in front of its star from our point of view, the star dims slightly. The amount of dimming reveals the planet's size relative to the star. The timing reveals the orbit. Repeated transits confirm that the event is periodic and not a passing instrument artifact. But stars are not perfect lamps. They pulse, rotate, flare, and carry dark star spots and bright faculae across their surfaces. Spacecraft drift. Detectors age. Cosmic rays strike sensors. Before a dip in brightness can become a planet, it has to survive the ordinary suspicion that astronomy applies to faint signals. Radial velocity looks for another kind of trace. A planet and a star orbit their common center of mass. The star's motion is small, especially when the planet is small, but it changes the star's spectrum by shifting spectral lines slightly toward blue as the star moves toward us and toward red as it moves away. The signal is a wobble in light, a rhythm in velocity. This method gives a minimum mass and helps distinguish a small rocky planet from a larger low-density world. It is also one reason hot Jupiters were discovered early, because large planets close to their stars create strong, fast signals. Finding an Earth twin with radial velocity is far harder. The Sun's motion caused by Earth is only about 9 centimeters per second. Direct imaging is the method that most resembles the human idea of seeing a planet, but it is among the most demanding. A planet is faint, and its star is bright. At visible wavelengths, an Earth-like planet near a Sun-like star would be overwhelmed by glare, like trying to see a firefly next to a searchlight from far away. Coronagraphs and starshades are designed to block the star's light, and adaptive optics correct for Earth's atmosphere from the ground. Direct imaging has already revealed some young, massive planets glowing in infrared light far from their stars. These images are not detailed landscapes, they are points. But those points are worlds, separated from their stars enough that their own light can be measured. Microlensing finds planets through gravity rather than repeated orbits. When a foreground star passes almost exactly in front of a more distant background star, the foreground star's gravity can bend and magnify the background light. If the foreground star has a planet, the planet can add a brief extra distortion to the lensing event. The method can detect planets far from their stars and even possibly free-floating worlds that drift without a star at all. But the alignment usually happens once. The event does not repeat on command, and follow-up can be difficult. It is a reminder that the census of planets depends not only on what exists, but on which observational windows happen to open for us. Astrometry is older in ambition and newer in its modern precision. It watches for the tiny side-to-side motion of a star on the sky as unseen companions tug it. The European Gaia mission has measured positions and motions of stars across the Milky Way with extraordinary accuracy, and its data continue to reshape knowledge of stellar neighborhoods. A planet's astrometric signal is small, but for certain systems it can reveal orbital inclination and true mass in ways other methods cannot. The long future of exoplanet science will not be built from one method replacing the others. It will be built from methods overlapping, correcting, and strengthening one another. Each technique has blind spots. Transits favor systems aligned edge-on from our point of view, and planets close enough to cross often. Radial velocity favors massive planets near their stars and bright, quiet stars whose spectra can be measured precisely. Direct imaging favors young, warm planets at wide separations. Microlensing favors distant alignments and does not usually allow repeated checks. Astrometry requires exquisite position measurements across time. A catalog of exoplanets is therefore not a neutral sample of everything in the galaxy. It is a catalog shaped by geometry, instrument sensitivity, stellar behavior, observing time, and the patience of people searching for signals that the universe does not make obvious. In the early years, every new planet seemed like an exception. Then the exceptions became patterns. Hot Jupiters were real, but not the most common kind. Super-Earths and sub-Neptunes appeared in large numbers. Compact systems around small stars became important targets. Planetary migration became central to explaining orbital architectures. Resonances showed how worlds could hold one another in gravitational rhythms. The alien part of alien worlds was no longer only that they orbited other suns. It was that they made the solar system feel less like a template and more like one outcome among many possible histories. Somewhere in this growing inventory may be a planet with an ocean under clouds, or beneath ice, or spread across a rocky surface under a sky with enough pressure to keep it liquid. Some worlds may have water only as vapor. Some may have lost it early to runaway greenhouse heating or stellar radiation. Some may hide it under global ice shells where sunlight never reaches. Some may have too much water, forming deep oceans above high-pressure ice that cuts the ocean off from rock and minerals below. Water matters because life on Earth uses it, but water alone is not life. It is a solvent, a medium, an environment. It creates possibility, not proof. The search for life has to begin with humility because Earth is still the only inhabited planet known with certainty. Every biosignature idea is tested against one example. Oxygen can come from life, but it can also accumulate under certain non-biological conditions. Methane can be biological, geological, or photochemical. A planet with both oxygen and methane in strong disequilibrium would be interesting because the gases react and should not coexist for long without renewal. But even then, the context would matter. A biosignature is not a label placed on a molecule. It is an argument built from a planet, a star, an atmosphere, a climate model, and the elimination of false positives. When a telescope records an exoplanet spectrum, it is not sampling air in the way a lander samples a planet. During a transit, a tiny fraction of starlight filters through the upper atmosphere of the planet if an atmosphere is present, and if clouds or hazes do not hide the features. Molecules absorb specific wavelengths. Those missing wavelengths create patterns in the spectrum. Carbon dioxide, water vapor, methane, sodium, potassium, and other species can leave fingerprints. The spectrum is a kind of shadow with chemistry inside it. But it is also blended with starlight, instrument behavior, and the atmosphere of the star itself. The line between discovery and overinterpretation can be thin. This is why the search for life beyond Earth moves slowly, even when the headlines move quickly. A possible molecule appears in a spectrum. Other teams reanalyze the data. Models change. New observations are requested. Stellar contamination is reconsidered. The planet's size and mass are revisited. The atmosphere may be interpreted one way under one set of assumptions and another way under a different set. Caution is not a lack of imagination. It is the method by which imagination is prevented from becoming a claim before the evidence can hold it. Long before a planet becomes a light curve, it begins as dust. In a young stellar nursery, a molecular cloud collapses into knots under gravity, and one of those knots becomes a star, surrounded by a disk of leftover material. The disk is not empty decoration around the birth of the star. It is raw planetary matter, silicate grains, metal, carbon compounds, ice beyond the frost line, gas drawn from the same cloud that made the star, and tiny particles that collide in orbit. At first, the collisions are gentle enough for grains to stick. Later, they become violent enough to shatter growing bodies apart. Out of this mixture, over hundreds of thousands and millions of years, planetesimals form, then embryos, then planets, though the path is not smooth and the disk does not wait forever. The location of a planet's birth matters because temperature changes the available building materials. Close to the young star, volatile compounds evaporate more easily, leaving rock and metal to dominate. Farther out, beyond the frost line, water and other ices can survive as solids, adding mass to growing cores. A core that grows quickly enough can gather hydrogen and helium from the surrounding disk before the gas disperses. This is one route to giant planets. But the disk is turbulent, magnetized, heated, cooled, and shaped by the growing planets inside it. Planet formation is not a simple assembly line. It is a race between growth, migration, collisions, gas loss, and the changing environment around a young star. The solar system carries a version of this story. Small rocky worlds close to the sun, gas giants farther out, ice giants beyond them. Small bodies in belts and reservoirs, left over from construction. For a long time, this arrangement seemed natural enough that it quietly became an expectation. Then exoplanets showed that nature had not been following the solar system as a preferred design. Giant planets could sit close to their stars. Super-Earths could orbit where nothing similar exists here. Compact systems could pack several worlds inside the orbit of Mercury. The architecture of a planetary system is not fixed by simple distance from the star. It is shaped by a history that may include movement as important as formation. Migration begins because planets interact with the disks in which they form. A young planet can exchange angular momentum with the surrounding gas, drifting inward or outward depending on conditions. Larger planets can open gaps in the disk. Multiple planets can push and pull one another into resonances, where their orbital periods lock into ratios. Later, after the gas is gone, gravitational encounters can scatter planets into elongated orbits or eject them entirely. Some worlds may have been born in systems they no longer belong to. A rogue planet moving between the stars may carry no sunrise, no seasons, and no visible parent star, only the heat it retained, the radio glow of auroras if it has a magnetic field, or the brief gravitational distortion it makes when it lenses a background star. A system's early violence can determine whether small, rocky worlds survive. Giant planets migrating inward may shepherd material, scatter embryos, or deliver volatiles. Collisions between planetary embryos can strip atmospheres or create moons. Earth's moon likely formed after a giant impact in the early solar system, though the details remain an active area of research. Around other stars, similar impacts may be common, but we usually cannot see them directly. We infer them from dusty debris disks, unusual compositions, or the absence and arrangement of planets. A planet that looks calm in a catalog may be the result of a past so violent that none of its original surface remains. Hot rocky planets show what happens when an orbit brings a world too close to its star. Some of these planets complete an orbit in less than one Earth day. Their day sides may become hot enough to melt silicate rock, forming lava oceans or vaporized mineral atmospheres. Their night sides, if they are tidally locked, may be cooler enough for minerals to condense. Winds could carry vaporized rock from the day side to the night side, where it falls back as exotic clouds or grains. These worlds are not habitable in any Earth-like sense, but they are laboratories in orbital extremes, revealing what gravity and radiation can do when a planet is held close to a star. Gas giants close to their stars can become inflated, their atmospheres puffed up by intense heating and perhaps internal processes that are still not fully understood. Some lose material into space, leaving comet-like tails of hydrogen. Observations in ultraviolet and infrared wavelengths can show atmospheric escape, chemistry, and heat redistribution. A hot Jupiter may be tidally locked, with fierce winds carrying energy from day side to night side. Weather on such a planet is not clouds over land and sea. It is circulation in a deep, irradiated atmosphere made mostly of hydrogen and helium, with temperatures high enough for chemistry unfamiliar at human scales. Super-Earths and sub-Neptunes are among the most important surprises of exoplanet science because they are common and ambiguous. A super-Earth might be a rocky planet larger than Earth. A sub-Neptune might be a rocky or icy core wrapped in a thick envelope of hydrogen and helium. Some may have deep water layers. Some may have lost their atmospheres, becoming stripped cores. Their radii and masses place them in a region where composition is not obvious. Two planets with similar sizes may be physically different. One could be dense and rocky, another could be lower density, volatile-rich, and wrapped in gas. Size alone does not tell the story. The so-called radius valley, a pattern in the distribution of small exoplanet sizes, suggests that many close-in planets are shaped by atmospheric loss. Planets below a certain size are often rocky, while those above it may retain thicker volatile envelopes. Stellar radiation can erode atmospheres, especially early in a system's life, when stars are more active. Internal heat can also drive gas escape. This means that the present-day planet is not simply what formed in the disk. It is what remains after billions of years of radiation, gravity, impacts, and chemistry have worked on it. A planet's atmosphere can be both shield and vulnerability. It warms a surface through greenhouse gases, moves heat, allows pressure for liquid water, and protects against some forms of radiation. But it can also be lost to space, stripped by stellar wind, eroded by impacts, or locked into rocks and oceans. A world too small may have trouble holding air over geological time. A world too close to its star may lose water through photodissociation, where ultraviolet light breaks water molecules and hydrogen escapes. Habitability is therefore tied to memory. A planet must not only receive the right amount of light now, it must have survived what happened before. Around young red dwarfs, this history becomes especially important. These stars can spend a long time in a brighter, more active early phase before settling into stable main sequence lives. A planet that sits in the habitable zone today may have spent its youth under stronger radiation, possibly losing oceans before the star quieted down. Yet red dwarfs are abundant and live for hundreds of billions or even trillions of years, far longer than the current age of the universe. If life can begin and persist around such stars, they could become the most common homes for biology in the galaxy. If their early activity sterilizes too many planets, abundance alone may not be enough. Tidal locking is sometimes treated as a simple barrier, but the physics is more subtle. A tidally locked planet keeps one face toward the star because gravitational interactions have slowed its rotation into synchrony with its orbit. Without an atmosphere or ocean, the day side could bake while the night side freezes. With enough air or water, heat can move. Climate models show possibilities: cloud decks over the substellar point reflecting light, winds carrying warmth into darkness, oceans distributing energy around the globe. But models depend on assumptions. The atmosphere must exist. The pressure must be right. The star's spectrum, flare activity, and the planet's rotation all matter. Planets around binary stars expand the idea of a sky. A circumbinary planet orbits two stars, crossing a region where gravitational stability depends on distance and the rhythm of the stellar pair. Kepler found such worlds through transits that did not repeat with simple spacing because the stars themselves were moving around one another. For a surface observer, if such a planet had a surface and a clear sky, sunrise would not belong to one sun. Shadows and seasons would be more complex. But again, the evidence begins as timing. A changing transit pattern, a brightness dip against two moving stars, a geometry solved from light. Some planetary systems are resonant chains where worlds orbit in linked ratios. TRAPPIST-1 is an important example, with 7 roughly Earth-sized planets in a compact arrangement around an ultra-cool dwarf star. Their mutual gravitational tugs help refine their masses, and their transits allow astronomers to study the system in detail. Several of its planets receive stellar energy levels that place them near traditional habitable zone conditions. The system is one of the most tempting nearby laboratories for rocky exoplanet atmospheres, but tempting does not mean easy. The star is small and active, the signals are subtle, and even with Webb, atmospheric interpretation remains difficult. A planet can also be too watery for certain forms of habitability. On Earth, the ocean touches rock. Chemical exchange between water, crust, mantle, atmosphere, and life helps sustain long-term cycles. Carbon dioxide is drawn down through weathering and returned by volcanism. Nutrients enter the ocean from continents, hydrothermal vents, and erosion. A deep global ocean on a larger planet might create high-pressure ice phases at the bottom, separating liquid water from rock. Such a world could still be interesting. It could still have chemistry. But the pathways that make Earth habitable would not automatically apply. Ocean planets in science fiction often appear as simple blue marbles, but real ocean worlds could vary enormously. Some might have shallow seas and continents. Some might have global oceans hundreds of kilometers deep. Some might be wrapped in hydrogen atmospheres with high pressures and warm surfaces. Others might hide oceans under ice shells, far from the warmth of their stars, heated from within by tides or radioactive decay. The word ocean does not name one environment. It names a phase of water, and water can occupy very different planetary stories. The first question for an ocean world is whether the ocean is stable. Liquid water requires pressure and temperature in the right range. A planet too cold at the surface may still hold liquid beneath ice if internal heat is sufficient. A planet too hot may lose water to space or keep it as steam. Atmospheric pressure changes boiling and freezing points. Salts and dissolved compounds alter freezing behavior. Tidal forces can knead interiors, creating heat. Habitability is physical before it is biological. A world must maintain environments where chemistry can persist long enough to become complex. The second question is energy. Life on Earth does not merely sit in water. It uses gradients, sunlight against darkness, oxidants against reductants, hot fluids against cold seawater, chemical disequilibrium maintained by geology, atmosphere, or metabolism. Photosynthesis transformed Earth's surface, but life existed before oxygen filled the atmosphere. And ecosystems near hydrothermal vents show that sunlight is not the only energy source available to biology. This is why icy moons matter. They prove that oceans can exist where sunlight is weak, if gravity and internal heat create the right conditions below the surface. The third question is chemistry. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, metals, salts, and many other ingredients all play roles in life as we know it. The presence of water is important because it dissolves and transports many compounds, but it does not guarantee the right inventory or concentrations. A planet's formation location, impacts, interior composition, atmosphere, and exchange with space can all affect chemistry. Searching for life means searching for context, not just one favored molecule. A single detection can be suggestive, but a living world would be a system. At a distance of dozens or hundreds of light years, context is hard. Even basic planetary properties can carry uncertainty. Radius comes from the size of the transit and the star's size. Mass comes from radial velocities or transit timing variations. Density comes from both, and composition is inferred from models. Atmospheric spectra are affected by clouds, hazes, stellar activity, and instrument limits. The farther the question moves from is there a planet to is there an ocean to is there life, the more carefully each step must be treated. The unknown does not disappear because the desire for an answer is strong. Yet the search continues because the clues are real. Young stars show disks where planets are forming. Mature stars show planets in astonishing variety. Some exoplanets are rocky. Some orbit in regions where surface water is possible. Some atmospheres can be measured. Some icy moons in our own solar system have subsurface oceans and active exchange between interior and surface. These facts do not prove life is common. They prove that the settings for possible life are not confined to one small blue planet around one ordinary star. The Kepler spacecraft did not travel from star to star. It stared. That was its great strength. For years, it watched one rich field in the direction of Cygnus and Lyra, recording the brightness of more than 100,000 stars with a patience no human eye could match. The images themselves were not spectacular in the usual sense. They were crowded star fields translated into numbers. What mattered was not a single beautiful frame, but the slow accumulation of brightness measurements across time. Somewhere in those measurements, planets crossed stars, and the crossings were small enough that they would have remained invisible without repetition. Kepler's contribution was not only the discovery of individual worlds, it changed the statistics of planets. By watching many stars in the same way, it allowed astronomers to estimate how common planets are, especially small planets in close orbits. It revealed that multi-planet systems are common. It showed that planets smaller than Neptune are abundant. It demonstrated that the galaxy is not merely sprinkled with planets, but deeply populated by them. When Kepler looked at a patch of sky that would fit under a hand held at arm's length, it found enough worlds to imply that the Milky Way should contain billions more. Kepler also taught astronomers how difficult certainty can be. A brightness dip can come from a planet, but also from a background-eclipsing binary star blended into the same pixels, or from a grazing stellar eclipse, or from instrumental effects. Candidates had to be vetted. Some were confirmed by radial velocity, some were statistically validated, some remained candidates for years. The catalogs grew through careful filtering, not simple announcement. This is why the language of exoplanet science distinguishes between candidates and confirmed planets. A signal can be promising without yet being secure. TESS, the Transiting Exoplanet Survey satellite, changed the search by looking across nearly the whole sky, focusing on bright nearby stars. Its planets are often better suited for follow-up because bright stars provide more light for spectroscopy and radial velocity measurements. TESS does not usually stare at one field, as long as Kepler did, which means it is especially good at finding shorter period planets, but its all-sky survey has become a map of nearby opportunities. If Kepler showed that planets are common, TESS helps identify which nearby systems can be studied in more detail with other instruments. A TESS detection may begin as a regular dip in a light curve. Then, ground-based telescopes observe the star during predicted transits to confirm that the dip occurs on the target and not on a neighboring star. Spectrographs may measure radial velocities to estimate mass. High-resolution imaging checks for close stellar companions that could confuse the signal. Stellar properties are refined because the planet's size depends on the star's size. The discovery of a planet is often less like a single moment and more like a chain of checks, each one removing an alternative explanation. Light curves are beautiful in a restrained way. They do not show mountains or clouds or seas. They show brightness against time, and the planet is visible only as a change in the star. A deep transit suggests a large planet relative to its star. A shallow transit suggests a smaller one. A long, flat-bottomed transit can indicate a full crossing, while a V-shaped dip may suggest a grazing event or stellar binary. Transit timing variations can reveal additional planets through their gravitational effects. In a system with multiple worlds, each planet becomes part of the other's evidence. Spectra are even more revealing and even more demanding. A spectrum spreads light by wavelength, turning a star into a pattern of lines and curves. Atoms and molecules absorb and emit at specific wavelengths because their electrons, rotations, and vibrations have allowed energy transitions. In stellar astronomy, spectra reveal temperature, composition, motion, and surface gravity. In exoplanet astronomy, spectra can reveal pieces of an atmosphere, but only when the signal is strong enough and the interpretation is careful enough. The planet is usually much fainter than the star, so the atmospheric signal may be a tiny difference between one measurement and another. During transmission spectroscopy, astronomers compare starlight when the planet is in front of the star with starlight when it is not. A small fraction of light filters through the limb of the planet's atmosphere, and molecules there absorb certain wavelengths. During eclipse spectroscopy, they measure the system when the planet passes behind the star, subtracting the star-only light from the combined star and planet light to estimate the planet's dayside emission or reflected light. Phase curves follow how the brightness changes through the orbit, revealing heat redistribution. A planet too distant to see as a disk can still have weather hinted at by the way its combined light rises and falls. The James Webb Space Telescope has made this work more powerful because it sees strongly in infrared wavelengths where many important molecular features appear. Its instruments can measure spectra of transiting exoplanets, probe hot giant atmospheres, and test rocky planets around small stars. Webb has already detected carbon-bearing molecules in the atmosphere of K2-18b and has examined planets in the TRAPPIST-1 system. But Webb is not a life detector. It is a telescope with extraordinary sensitivity, and its results still depend on repeated observation, careful calibration, and models that account for stars as well as planets. For rocky planets around red dwarfs, the star can become part of the difficulty. Star spots in bright regions can alter the apparent spectrum during a transit. If the planet crosses one part of the star while other regions remain unocculted, the measurement can carry features of the star that resemble or obscure atmospheric signals. This problem, called stellar contamination, is not a minor technicality. For the small signals of Earth-sized planets, the star's surface may be loud enough to confuse the planet's air. The search for an atmosphere can become a search for how well the star is understood. In direct imaging, the challenge is different. The star must be suppressed enough for the planet's faint light to emerge. Coronagraphs inside telescopes reshape and block starlight. Starshades, proposed for future missions, would fly far from a telescope and cast a carefully shaped shadow, reducing diffraction so that planets near bright stars can be seen. Ground-based observatories use adaptive optics, measuring atmospheric distortion and correcting it with deformable mirrors many times per second. The goal is not only to find a point of light, it is to separate that point from glare and then spread it into a spectrum. A directly imaged Earth-like planet around a nearby Sun-like star would be one of the most important observations in the history of astronomy, but it would still appear as a point. Its color and spectrum might reveal oxygen, ozone, water vapor, methane, carbon dioxide, clouds, and surface hints if the signal were strong enough. Repeated observations might show rotation, seasons, changing cloud patterns, or the red edge of vegetation like pigments if such pigments existed. Every one of those possibilities comes with caveats. The planet would be far away, the light faint, and the models uncertain. Still, the first pale point from another Earth-like world would change the emotional scale of the search. Data archives have become part of the discovery environment. A spacecraft may complete its mission, but its observations remain. New methods can return to old light curves and find signals that were missed, especially as machine learning improves and as stellar behavior becomes better modeled. Candidate lists are revisited, false positives are removed, new planets are added. Astronomy is not only telescopes under the night sky, it is also servers, calibration files, old pixels, updated catalogs, and researchers comparing one version of the evidence against another. The search is limited by time as much as by sensitivity. A planet like Earth transits the Sun once per year from the right alignment. To confirm such a planet by transit, several years of observation may be needed. Longer period planets require longer patience. Direct imaging may find wider orbit planets more easily, but observing enough orbital motion to understand them can take years or decades. Radial velocity signals from distant analogs of Jupiter need long baselines. Planetary systems unfold on orbital timescales, and human observing programs have to fit themselves into those rhythms. Some stars are easier hosts for observation than others. Quiet stars with stable brightness and sharp spectral lines are better for precise measurements. Bright nearby stars offer more photons. Small stars make planetary transits deeper because the same planet blocks a larger fraction of the star's disk. But small stars can be active, and activity complicates atmospheric searches. There is no perfect target. Every star gives something and takes something away. The concept of the habitable zone is most useful when it is not treated as a guarantee. A planet inside it may lack an atmosphere. A planet outside it may hide a subsurface ocean. A planet on its inner edge may run into greenhouse heating that evaporates oceans. A planet on its outer edge may require enough carbon dioxide to stay warm, but too much can alter chemistry and climate in ways that are hard to predict. Even the boundaries are model-dependent, because clouds, rotation, atmospheric composition, continents, oceans, and stellar spectrum all matter. Earth's history shows that habitability is not static. The young sun was fainter than it is now, yet early Earth had liquid water. The atmosphere changed through volcanic outgassing, weathering, biological activity, impacts, and escape to space. Oxygen became abundant only after life had already existed for a long time, and the rise of oxygen was itself a planetary transformation. Snowball Earth episodes may have covered much of the planet in ice. Mass extinctions changed the biosphere without ending it. If Earth were observed from far away at different times, it would not present the same atmospheric signature in every era. This matters because a living planet is not always easy to recognize. For much of Earth's history, there were no forests, no animals, no cities, and no strong oxygen-rich atmosphere. Microbial life altered chemistry in ways that took time to become globally obvious. A telescope looking at early Earth from a distance might not have seen the biosignature combination that would make modern Earth stand out. A planet can be inhabited and still quiet to our instruments. The absence of an obvious signal is not the same as absence of life. The reverse is also true. A planet can produce misleading signals without biology. Ultraviolet light can split water vapor, allowing hydrogen to escape and oxygen to build up abiotically under some conditions. Carbon monoxide can persist in atmospheres with limited chemistry and complicate interpretation. Methane can come from hydrothermal reactions as well as organisms. Dimethyl sulfide, discussed in relation to K2-18b, is associated with life on Earth, but possible detection and possible interpretation are not the same as confirmation. The most dangerous word in the search for life is proof when the evidence only supports interest. Scientists therefore look for combinations: oxygen with methane, water with carbon dioxide under plausible temperatures, surface pressure constraints, stellar ultraviolet behavior, planetary mass and radius, signs of clouds or hazes, the age of the system, the possibility of volcanic outgassing, the presence or absence of hydrogen-rich envelopes. Each piece narrows the range of explanations. A convincing biosignature will likely be cumulative, not isolated. It may arrive as a case built slowly from many observations, each one surviving attempts to explain it without life. There is a human difficulty in this slow approach. The question is enormous, and the measurements are small. We want a direct answer, but the universe offers partial evidence through instruments. A spectrum with a possible molecule is exciting because it points toward a world, but it is also fragile because the signal may depend on calibration, stellar models, cloud assumptions, and retrieval methods. The discipline required is part of the wonder. Exoplanet science has become powerful not by pretending the uncertainties are absent, but by measuring them. Even the word alien needs caution. An alien world is not necessarily strange because it is theatrical. It is strange because it formed elsewhere, under another star, with a history we can only reconstruct from light. A planet with no life can still be alien in the deepest physical sense. A planet with a hydrogen envelope, a magma ocean, a resonance with neighboring worlds, or an atmosphere escaping into space is not a symbol. It is a real object moving under gravity. The search for life rests on this realism. Before asking whether a world is alive, scientists must ask what kind of world it is. The Milky Way does not make this easy. Dust hides regions of star formation. Stars crowd together. Distance dims light with the square of separation. The galaxy rotates, evolves, and contains stellar populations of different ages and chemical compositions. Planets around metal-rich stars may form differently from planets around stars with fewer heavy elements, because planets require materials forged by earlier generations of stars. Every rocky planet carries the ashes of dead stars in its crust. Every ocean contains elements made before its star was born. The elements necessary for planets were not present in the earliest universe in useful abundance. Hydrogen and helium dominated after the Big Bang, with trace amounts of lithium. Heavier elements came later, built inside stars and distributed by stellar winds, supernovae, and neutron star mergers. Carbon, oxygen, silicon, iron, phosphorus, and many other elements needed for rocky worlds and life were cosmic products before they were planetary ingredients. The search for life is therefore tied to cosmic history. A living planet requires not only a star and an orbit, but earlier generations of stars that enriched the galaxy enough for rock, water, and chemistry to exist. Planetary habitability also depends on time. Life on Earth appears to have emerged relatively early in the planet's history, though the details of origin remain unresolved. Complex life took far longer. Technological life, at least here, arrived very late. Around other stars, planets may be too young, too old, too unstable, or perfectly ordinary. A world might host microbes for billions of years and never develop complex organisms. The search for life should not silently assume that biology, oxygen, intelligence, and technology are one inevitable ladder. Earth shows one path, not every path. Looking at exoplanets makes Earth both less central and more specific. It is not the only planet. It is not the largest, oldest, or most common kind of world. Yet, it remains the only place where oceans, continents, atmosphere, geology, and life are known to have worked together for billions of years. That makes Earth not a cosmic exception to be worshipped, but a reference case to be studied carefully. Its details are not distractions from the search. They are the search's foundation. Before the search moves fully outward to planets around other stars, it has to pass through the ocean worlds closer to home. Europa is only a moon of Jupiter, and Enceladus is only a moon of Saturn, but those words can make them sound smaller in importance than they are. Both are worlds with ice-covered surfaces and strong evidence for liquid water beneath. They are not warm blue planets in the sunlight. They are cold, bright, airless, or nearly airless bodies in the outer solar system, surrounded by radiation, gravity, and darkness. Yet under their frozen crusts may be environments where water touches chemistry, where energy may be available, and where the question of life becomes less remote than the distance to another star. Europa's surface is young by geological standards, crisscrossed with dark lines, ridges, disrupted blocks, and regions where the ice appears to have moved, cracked, and refrozen. The surface has relatively few large impact craters compared with many other icy bodies, suggesting renewal. Beneath that surface, multiple lines of evidence point toward a global ocean. Magnetic measurements from the Galileo spacecraft, surface geology, density estimates, and models of tidal heating. Jupiter's gravity pulls on Europa as it orbits, and the resonance with neighboring moons helps keep the orbit slightly eccentric. That changing gravitational stress flexes Europa's interior and supplies heat. The ocean is not warmed by sunlight from above, but by energy generated through motion and gravity. Europa is not easy to study from Earth. It is small, distant, and embedded in the powerful magnetic environment of Jupiter. Charged particles trapped around Jupiter strike Europa's surface, altering molecules and darkening some regions. This radiation makes the surface hostile to life as we know it, but it may also create oxidants that could be transported downward through cracks or overturning ice, potentially feeding chemical reactions in the ocean below. The same environment that damages molecules at the surface could help create chemical imbalance. If surface material can reach the water beneath. The Europa Clipper mission was built to study this possibility in detail. Launched in 2024, it is traveling toward the Jupiter system and is designed to make dozens of close flybys of Europa after arrival. It will not land, and it is not designed to directly find living organisms. Its goal is habitability, the thickness and behavior of the ice shell, the depth and salinity of the ocean, the chemistry of the surface, the presence of possible plumes, and the exchange between surface and interior. That distinction matters. A mission can transform knowledge of a world without making a life detection. It can tell scientists whether the necessary conditions are plausible enough to justify the next question. A camera sees a cracked plane. An ice-penetrating radar listens for boundaries below the surface. A magnetometer measures how Europa interacts with Jupiter's magnetic field. Spectrometers identify compounds on the surface. A dust analyzer samples particles thrown into space by impacts or activity. Each instrument sees the moon differently, and the moon only becomes more understandable when those views are combined. Europa is not a single mystery waiting for one answer. It is a physical system, with ice, ocean, rock, salts, radiation, and tides all acting over long periods of time. Enceladus is smaller than Europa, yet in one way it has been more generous. It throws pieces of its ocean into space. Cassini saw plumes erupting from fractures near the South Pole, the so-called tiger stripes, where water vapor, ice grains, salts, organic compounds, and other materials escape into Saturn's system. The spacecraft flew through those plumes and sampled them directly with instruments not originally designed as life detectors, but powerful enough to reveal chemistry. For astrobiology, this was extraordinary. A subsurface ocean did not have to be drilled into. It was leaking upward into the path of a passing spacecraft. The chemistry of Enceladus points toward water-rock interaction. Hydrogen detected in the plume material suggests processes that may resemble serpentinization, where water reacts with certain rocks, producing hydrogen that microbes on Earth can use as an energy source. Silica particles indicate hot water interacting with rock. Salts suggest an ocean in contact with a rocky core rather than isolated pure ice. None of these observations proves life exists there. But they show that Enceladus is not just a ball of ice with water inside. It has active chemistry, an ocean, and energy sources of the kind that make scientists pay attention. Tidal heating is central to Enceladus as well. Saturn's gravity, along with orbital interactions with other moons, flexes the small world enough to maintain internal heat. The south polar terrain is warmer and more active than the rest of the moon. The plumes feed Saturn's E-ring, making Enceladus a world that visibly alters its environment. A moon only about 500 kilometers across is continuously supplying material to a ring around a giant planet. In the scale of the solar system, small does not mean inactive. Titan, another moon of Saturn, adds a different kind of ocean world to the story. Its surface is not covered by liquid water because it is far too cold. Instead, Titan has lakes and seas of methane and ethane under a thick nitrogen-rich atmosphere. It has rain, rivers, dunes, clouds, and complex organic chemistry driven by sunlight and particles in Saturn's environment. Beneath its icy crust, evidence also suggests a water ocean. Titan may not be habitable at its surface in the Earth-like sense, but it is one of the richest chemical laboratories in the solar system, and its subsurface water adds another layer to the question. Ganymede and Callisto, large moons of Jupiter, may also contain subsurface oceans. So may some distant bodies beyond Neptune, including Pluto, based on geological evidence and thermal models. The outer solar system may be filled with worlds where liquid water exists beneath ice, far from the traditional habitable zone. This does not mean life is everywhere. It means that liquid water is not restricted to Earth like surfaces warmed by sunlight. Gravity, radioactive decay, antifreeze chemistry, and thick ice shells can create hidden reservoirs. The discovery of subsurface oceans changed the meaning of habitability. Before them, the search naturally focused on the surface of planets in the right orbit around a star. That remains important, especially for exoplanets, because surface conditions influence atmospheric signatures. But icy moons show that life, if it can operate without sunlight, may have possible habitats hidden under surfaces that look unwelcoming from above. A frozen exterior can conceal a liquid interior. A world can appear dead to a camera and still possess chemistry in darkness below. On Earth, the deep ocean is not lifeless where sunlight disappears. Hydrothermal vents support ecosystems built on chemical energy. Microbes use reactions involving hydrogen sulfide, methane, iron, and other compounds. Life occupies basaltic crust, sediments, ice, acidic springs, salty lakes, and environments once thought too extreme. These facts do not prove that life begins easily in such places, but they expand the kinds of environments that can sustain it once it exists. Astrobiology uses extremophiles carefully, not as proof of alien life, but as evidence that Earth's biology can work across a wider range of conditions than human comfort would suggest. The origin of life is still unsolved. Scientists study possible pathways involving hydrothermal vents, wet-dry cycles, mineral surfaces, ice, ultraviolet chemistry, RNA-like molecules, metabolism-first networks, and many other possibilities. Different environments provide different advantages. Hydrothermal systems offer energy and mineral catalysts. Surface ponds may allow concentration through evaporation. Ice can protect molecules and concentrate solutes in brines. Because the origin remains uncertain, the best habitat for sustaining life may not be the same as the best habitat for starting it. This uncertainty matters when comparing Earth-like planets with icy moons. For exoplanets, subsurface oceans are difficult to detect directly. A moon like Europa around another star would be almost impossible to characterize with current technology unless it produced a detectable effect through its planet or star. Surface ocean planets are more accessible because they can affect a planet's atmosphere, reflected light, and climate. Observational bias therefore shapes the search for life. The habitats easiest to study may not be the only habitats that exist. The universe may hide many ocean worlds that leave almost no sign from interstellar distances. A true ocean planet around another star might reveal itself through density, atmospheric composition, climate behavior, and reflected light. A low-density planet in a certain mass radius range may contain large amounts of water or gas, but mass and radius alone are ambiguous. Water vapor in an atmosphere can indicate water, but not necessarily an ocean. Clouds can hide lower layers. Hydrogen-rich atmospheres can produce strong spectral features that are easier to observe, but they may belong to worlds unlike Earth. The word ocean can be tempting because it feels familiar. The evidence for an exoplanet ocean is usually indirect. K2-18b became important partly because it sits in this ambiguity. It is larger and more massive than Earth, smaller than Neptune, and orbits in the habitable zone of a cool dwarf star. Webb observations found methane and carbon dioxide in its atmosphere, and the data have been discussed in relation to the Hycean hypothesis, a hydrogen-rich atmosphere above a water ocean. There has also been discussion of possible dimethyl sulfide, a molecule associated with life on Earth, though the inference has required further validation and remains debated. This is exactly where scientific restraint matters. The planet is fascinating. That is not the same as inhabited. A Hycean world, if it exists, would not be an Earth twin. It could have a deep global ocean beneath a hydrogen atmosphere with high pressures and climate regimes unfamiliar in the solar system. Such worlds might offer stronger atmospheric signals than small rocky planets because their atmospheres are extended and easier to probe during transits. That makes them attractive observational targets, but their interiors are uncertain. High-pressure ice, ocean temperature, atmospheric mass, and chemical exchange with rock could determine whether they are truly habitable or only appear inviting from a distance. The phrase water world can also conceal danger. Too much greenhouse heating can push water into vapor, making a steam atmosphere that drives hydrogen escape. Too much pressure can alter chemistry. Too little geological cycling can limit nutrients. Too much stellar activity can erode air or alter molecules. A global ocean without continents may have fewer weathering feedbacks than Earth, though seafloor weathering may still matter. Habitability is not maximal water. It is the right kind of water in contact with the right sources of energy and chemistry over enough time. There is a reason scientists often return to Europa and Enceladus even when the title is Exoplanets. They are nearby examples of hidden habitability. They show that ocean worlds can form and persist. They reveal how ice shells, tides, and rock-water chemistry might work. They give missions a chance to test instruments, sampling strategies, and biosignature concepts in places reachable by spacecraft. The search beyond the solar system is stronger when it is grounded in what nearby worlds teach us. A lander on an icy moon would face a very different problem from a telescope studying an exoplanet. It would have to survive cold, radiation, uncertain terrain, and contamination control. It would need to sample ice or plume fallout without bringing Earth microbes along in a way that confuses the question. It would search for patterns in amino acids, lipids, isotopes, cell-like structures, or chemical disequilibrium. Direct sampling has power, but also responsibility. A false positive from contamination would be more than an error. It would damage one of the most important investigations humans can attempt. For a telescope, contamination has another meaning. It is not microbes, but starlight, detector noise, foreground dust, background stars, and assumptions inside models. The instrument never touches the planet. It receives photons that have crossed space, passed through optics, struck detectors, and been processed into data. Both approaches, the lander and the telescope, share a discipline, knowing what else could produce the signal before calling it life. If life exists in an ocean under ice, it may not change the surface dramatically. It may be microbial, sparse, local, and chemically subtle. It may live near hydrothermal systems or within porous rock. It may leave molecules that degrade before reaching the surface. It may have no atmosphere to alter. The nearest inhabited place beyond Earth, if it exists, could be quiet enough that only a careful sample from the right depth would reveal it. The universe is under no obligation to make life visible. The same is true for exoplanets. A living ocean planet may produce a weak atmospheric signal. A lifeless planet may produce a stronger false one. A world with clouds may hide its lower atmosphere. A planet around an active star may have spectra dominated by stellar behavior. Searching for life is not merely searching for excitement, it is searching for evidence strong enough to survive disappointment. This is why ocean worlds occupy such an important middle ground. They are neither simple promises nor empty speculation. They are physical places where water, energy, and chemistry can be investigated. Europa, Enceladus, Titan, and distant exoplanet candidates all show different versions of the same broader idea. Habitability is not one landscape. It is a set of conditions that can appear in more than one kind of world. The challenge is learning which versions are common, which are rare, and which, if any, become living systems. An atmosphere is the most accessible part of an exoplanet, and also one of the easiest to misunderstand. It is the layer that light can touch before reaching us. It can carry gases from volcanoes, oceans, rocks, impacts, escape, and living organisms if life is present. It can hide a surface entirely or expose it to radiation. It can make a planet warm enough for liquid water or push it into runaway heat. To know an atmosphere is to know the boundary between a planet and space, but the boundary is not simple. It is chemistry in motion, constantly changed by light, temperature, gravity, and time. On Earth, the atmosphere is not just a mixture of gases, it is a record of planetary history. Nitrogen dominates. Oxygen is abundant because photosynthetic life changed the planet. Carbon dioxide is present in small amounts but controls climate powerfully. Water vapor responds to temperature and weather. Methane is unstable in oxygen-rich air and therefore must be replenished. Ozone forms from oxygen under ultraviolet light and protects the surface from some radiation. From far away, modern Earth would look chemically unusual because its atmosphere is not in simple equilibrium. It is being maintained by geology and life together. A biosignature gas must be considered in that larger context. Oxygen is often discussed because it is abundant in modern Earth's atmosphere and strongly associated with photosynthesis. But oxygen can also arise when water is broken by ultraviolet light and hydrogen escapes to space, especially under some planetary and stellar conditions. Ozone can indicate oxygen, but it can be affected by photochemistry. Methane can indicate biology, but it can also be produced by geological reactions. Nitrous oxide may be biological on Earth, but difficult to detect in many cases. No molecule carries a universal label that says, "Life made me." The strongest atmospheric biosignatures are likely to involve disequilibrium. A planet with gases that should react away, but persist together, suggests an active source. Oxygen and methane are the classic example, because methane in an oxygen-rich atmosphere has a limited lifetime. If both were detected in substantial amounts on a temperate rocky planet with water vapor, the case would be important. But even then, scientists would ask about volcanoes, photochemistry, impacts, atmospheric escape, surface sinks, and stellar ultraviolet radiation. A biosignature is not a single observation. It is a surviving explanation after non-biological alternatives have been tested. False positives are not failures of the search. They are part of the search. A planet around a small active star might lose water early, leaving oxygen behind without life. A dry planet with little volcanic outgassing might accumulate oxygen differently. Carbon monoxide can provide clues because some abiotic oxygen scenarios produce it as well. The absence of expected companion gases can weaken a claim. Context is a filter. It does not remove uncertainty entirely, but it prevents one exciting line in a spectrum from carrying more meaning than it deserves. False negatives are just as important. A living planet may not produce detectable oxygen. Early Earth did not for a long time. An ocean world under ice may have life that never communicates strongly with an atmosphere. A planet with an atmosphere full of clouds or haze may hide its lower chemistry. A biosphere could be weak, local, or chemically unlike Earth's surface biosphere. The universe could contain life that is real, but observationally quiet. The limits of our instruments are not the limits of nature. The spectral search is made harder by clouds and hazes. Clouds can flatten transmission spectra by blocking starlight from passing through deeper atmospheric layers. Hazes can scatter light and mimic slopes or hide molecular features. On some planets, photochemical hazes may form under ultraviolet radiation, especially in atmospheres rich in methane or other hydrocarbons. Titan is a nearby example of a world whose surface is hidden under a thick orange haze. Around another star, a haze may turn a potentially rich atmospheric spectrum into a nearly featureless line. Pressure also matters. A molecule can absorb light differently depending on temperature, pressure, and the presence of other gases. Collision-induced absorption, where molecules absorb light during interactions, can reveal bulk atmospheric properties in some cases. Broad spectral bands can overlap. Retrieval models attempt to infer atmospheric composition from the observed spectrum, but many combinations can sometimes fit the data. A retrieval is not a photograph of the atmosphere, it is a model-based interpretation of limited light. For hot Jupiters, spectra are often stronger because the planets are large, their atmospheres extended, and their transits deep. Astronomers have detected water vapor, sodium, carbon monoxide, carbon dioxide, methane in some cases, and signs of thermal inversions or clouds. These planets are not good candidates for life, but they teach the techniques. They reveal atmospheric circulation under extreme irradiation and provide test cases for models. Before scientists can read the faint atmosphere of a small temperate planet, they practice on larger, brighter, easier worlds. Warm Neptunes and sub-Neptunes occupy an important middle region. Their atmospheres can be easier to observe than those of rocky planets, but their physical nature is often uncertain. Are they gas-rich mini-Neptunes, water-rich worlds, rocky cores with thick envelopes? Their spectra may show methane, carbon dioxide, water, or hazes, but mass and radius are needed to interpret the atmosphere. A planet cannot be understood by its spectrum alone. Its density, orbit, star, and possible interior structure all shape the meaning of the gases. Rocky exoplanet atmospheres are the hardest and most desired. A terrestrial planet around a sun-like star has a small transit signal and a thin atmosphere. Around a red dwarf, the smaller star makes transits deeper, but stellar activity becomes more challenging. Webb's thermal emission measurements of the innermost TRAPPIST-1 planets have suggested that some may lack thick atmospheres, at least for the planets closest to the star. That does not settle the entire system. It shows how observations can begin to distinguish bare rock from air, and how difficult the outer, cooler planets remain. A bare rock can still be scientifically valuable. If a planet has no atmosphere, that result teaches about atmospheric loss, stellar radiation, formation, and volatile delivery. The absence of air around one world helps constrain what happened in the system. If close-in planets are stripped, outer planets may still retain atmospheres, or they may share a volatile poor history. Exoplanet science is not only the search for Earth, it is the study of why some worlds become Earth-like, why others become Venus-like, Mars-like, Neptune-like, or something the solar system never produced. The search for water vapor is emotionally powerful because water is tied so strongly to life on Earth. But water vapor in an atmosphere does not necessarily mean oceans on the surface. It can come from steam, high-altitude moisture, outgassing, or a deep volatile layer. Conversely, a planet with oceans may show little water vapor if the atmosphere is cold or cloudy. Water is important, but it must be placed in a climate. Temperature, pressure, clouds, stellar spectrum, and atmospheric circulation all determine whether water is ocean, ice, vapor, or hidden reservoir. Carbon dioxide can be a climate regulator or a warning sign. On Earth, it participates in the long-term carbonate-silicate cycle, which helps stabilize climate over geological time. On Venus, carbon dioxide dominates a dense atmosphere and contributes to extreme greenhouse heating. On Mars, it forms a thin atmosphere unable to keep the surface warm enough today for stable liquid water under most conditions. The same molecule can belong to very different planetary outcomes. Its meaning depends on amount, pressure, distance from the star, and planetary history. Methane draws attention because life produces much of Earth's atmospheric methane, but methane is not exclusively biological. It can form in hydrothermal systems through reactions involving water and rock, from impacts, or through photochemistry under certain atmospheric conditions. On a planet with little oxygen, methane can persist longer and build up without requiring the same renewal rate as on modern Earth. Detecting methane would be interesting. Detecting methane in a full planetary context where non-biological sources fail would be far more important. Dimethyl sulfide and related sulfur compounds became widely discussed because, on Earth, DMS is produced mainly by marine life, especially planktonic organisms. In the context of K2-18b, possible spectral features prompted excitement, but the interpretation remains unsettled, and other analyses have urged caution. Even if a sulfur-bearing molecule were confirmed, the question would not end. Scientists would need to know whether that molecule can form abiotically under the planet's conditions, whether the spectrum truly requires it, and whether other expected gases are present or absent. Pigment signatures are another possible pathway. Plants on Earth reflect strongly in near-infrared wavelengths, producing the vegetation red edge. Other photosynthetic organisms use different pigments, and life under another star might adapt to that star's spectrum. A red dwarf emits more of its energy in infrared than the Sun does, which could change the useful wavelengths for photosynthesis. A living surface might have a spectral edge, but it might not be red in the Earth sense, and clouds or oceans could hide it most of the time. Seasonal changes could provide context. On Earth, carbon dioxide, vegetation reflectance, cloud patterns, and atmospheric composition vary with seasons. A distant observation of a rotating and orbiting planet might reveal periodic changes connected to surface and climate. But to see such details, a telescope would need to collect enough photons and separate the planet from the star over time. The signature would not be a landscape. It would be a pattern of changing color and brightness, interpreted through models. Technosignatures form a separate branch of the search. They include radio signals, optical laser pulses, unusual atmospheric pollutants, waste heat, city-like nightlights, or large-scale structures. Though many of these are far beyond current detection for Earth-like levels of technology at interstellar distances. Radio searches have scanned parts of the sky for narrowband signals that nature is not expected to produce easily. So far, there is no confirmed technosignature. The absence is meaningful only within the limits of where, when, and how searches have looked. The radio sky is not empty. It contains pulsars, magnetars, quasars, planetary emissions, human interference, satellites, radar, and noise. A candidate's signal must be checked against local interference, repeated, localized, and examined across frequencies. The famous WOW signal remains a historical example of an intriguing event that did not repeat and therefore could not become evidence of another civilization. In science, a signal that cannot be checked remains a question, not a discovery. Optical SETI looks for brief laser-like pulses, and future instruments may expand the search for artificial atmospheric compounds or waste heat. Yet technosignatures come with an even deeper uncertainty than biosignatures. Life may be microbial for most of its history. Technology may be rare, short-lived, quiet, or expressed in ways humans do not anticipate. Civilizations, if they exist, may not broadcast continuously or use communication methods that leak into space. A silent sky does not prove we are alone. It proves that under the searches conducted so far, no confirmed signal has survived. The Drake equation is often treated as a way to estimate civilizations, but its lasting value may be as a map of ignorance. Star formation rate, fraction of stars with planets, number of habitable planets, fraction where life begins, fraction where intelligence develops, fraction that becomes detectable, and length of detectable lifetime all matter. Some terms are now better constrained than before, because exoplanets are known to be common. Others remain almost entirely unknown, because Earth is the only biological example. The equation is not a calculator with a reliable answer. It is a framework showing which questions must be answered before the galaxy's silence or abundance can be understood. Biosignature science works in a similar way. It identifies what would make a planet interesting, what observations are needed, what false positives must be excluded, and what instruments could gather the data. It does not promise an easy discovery. Some of the most important work happens before any claim, in laboratories measuring molecular spectra, in climate simulations, in studies of ancient Earth, in experiments on extremophiles, in models of atmospheric escape, and in mission designs that ask what evidence would be convincing. The search for life is built from preparation as much as observation. Ancient Earth is one of the most important analogs. Its atmosphere changed from low oxygen to oxygenated. Its oceans changed chemistry. Its continents grew and reorganized. Life began as microbes and stayed microbial for most of the planet's history. The Great Oxidation Event altered the atmosphere roughly 2.4 billion years ago, long after Earth formed. If oxygen is the biosignature easiest for some future telescopes to detect, then Earth itself warns us that inhabited planets may spend long eras without presenting that signature strongly. Venus is another warning. It may once have had more water, though the details are debated. Today it has a dense carbon dioxide atmosphere, crushing pressure, extreme temperatures, sulfuric acid clouds, and a dry surface. From a distance, a Venus-like exoplanet might be close in size to Earth and near the inner region of habitability if only crude measurements were available. A planet can be Earth-sized and profoundly un-Earth-like. Radius is not destiny. Mars is a different warning. It has river valleys, deltas, minerals formed in water, and strong evidence that liquid water once existed on its surface. Today it is cold, dry, and thin-aired, with most of its surface exposed to radiation and oxidizing chemistry. Its habitability, if it ever supported life, may have been ancient and limited. A planet can pass through a habitable phase and leave it behind. Observing a world now may not reveal what it once was. These nearby worlds make the exoplanet search more careful. They show that water, atmosphere, size, and orbit interact over time. They show that neighboring planets can follow very different paths under the same star. Venus, Earth, and Mars formed in one system from related materials, yet their surfaces diverged dramatically. Around another star, 3 small planets might look similar in a catalog and still represent 3 separate planetary fates. A future biosignature claim will probably have to answer several questions at once. Is the planet truly rocky, or does it have a thick volatile envelope? Is it in a temperature range where liquid water could exist? Does it have an atmosphere? Are the gases reliably detected? Could the star produce or mimic the signal? Could geology explain it? Could photochemistry explain it? Are clouds hiding crucial context? The answer may arrive not as one announcement, but as a gradual tightening of possibilities until life becomes the best remaining explanation. That would be a different kind of discovery from the first exoplanet. The first planet beyond the solar system could be confirmed by dynamics. Life requires interpretation of a system. The standard of evidence will be higher because the claim is larger. A planet can be confirmed by a wobble. A biosphere has to be inferred from the behavior of matter over time. Still, there is something powerful about the fact that the search has reached this level. Astronomers are no longer only asking whether other worlds exist. They are asking what their air contains. They are testing whether oceans might lie under ice or under hydrogen atmospheres. They are designing telescopes not merely to count planets, but to ask whether any of them resemble the living Earth in measurable ways. The question that once belonged mostly to philosophy has become an observing program. Some systems become landmarks because they concentrate many questions in one place. TRAPPIST-1 is one of them. The star is small, cool, and faint, an ultra-cool dwarf only a little larger than Jupiter, but massive enough to fuse hydrogen. Around it move 7 planets with sizes broadly similar to Earth. They orbit close to the star, much closer than Mercury orbits the Sun, yet because the star is so dim, several receive amounts of energy that make them important targets in discussions of habitability. A planetary system that would fit comfortably inside the inner solar system contains 7 rocky-sized worlds, each crossing the face of its star from our point of view. The geometry of TRAPPIST-1 is unusually helpful. Because the planets transit, their radii can be measured. Because they tug on one another gravitationally, their transit times shift slightly, and those shifts help constrain their masses. With mass and radius, astronomers can estimate density. The planets are also locked in a chain of near resonances, so their orbits are not isolated. The system behaves like a set of clocks that subtly disturb one another, and those disturbances carry information about worlds too small and distant to see directly. But helpful geometry does not remove the hard questions. TRAPPIST-1 is an active red dwarf. Its planets orbit close enough that tidal locking is likely. Their atmospheres, if they exist, have endured stellar radiation, flares, and long exposure to a star whose early history may have been intense. Webb observations of the innermost planets have begun to test whether thick atmospheres are present, with results suggesting that some close-in worlds may be bare or lack substantial heat redistributing atmospheres. Yet the more temperate outer planets remain difficult. The most interesting targets are often the hardest. A planet called TRAPPIST-1e is often discussed because its estimated irradiation and density make it one of the more Earth-like candidates in the system. But Earth-like in this context does not mean Earth. It means roughly similar size, possibly rocky composition, and stellar energy in a range where liquid water is not immediately impossible. It does not tell us whether there is air, ocean, plate tectonics, magnetic protection, or life. The name of the category is doing less work than the measurements behind it. Proxima Centauri b has a different importance because it orbits the nearest star to the Sun. At a little over 4 light-years away, Proxima Centauri is close by astronomical standards, yet still far beyond current spacecraft reach in any ordinary sense. The planet was found through radial velocity, the tiny motion it induces in the star. It receives an amount of stellar energy that puts it in discussions of possible habitability, but its star is an active red dwarf, and the planet's atmosphere is unknown. The nearest potentially temperate exoplanet is still a world we cannot see as a surface. Nearness does not make it accessible. If Proxima Centauri b transited, it would be easier to study, but its orbit does not appear to be aligned that way from Earth. That means no regular shadow crossing the star for telescopes to use. Without transits, radius and atmosphere are harder to measure. Future direct imaging or extremely precise instruments may improve the situation, but for now the planet is a reminder that the most interesting worlds do not always arrange themselves conveniently. The galaxy is not designed around our observing methods. Kepler-186 Fief was important because it was one of the first Earth-sized planets found in the habitable zone of another star. Its discovery showed that small planets in potentially temperate orbits were not merely theoretical targets. But it is distant, and its atmosphere is unknown. Kepler-452b, sometimes described as a larger cousin of Earth, drew attention for orbiting a Sun-like star in a long-period orbit, but its size suggests it may be a super-Earth or mini-Neptune, and its true nature remains uncertain. The public names are memorable, but the science stays cautious because a radius and an orbit are only the beginning. TOI 700, LH 1140, and other nearby red dwarf systems have become valuable because they offer small planets around stars bright enough for follow-up. Some candidates sit in or near habitable zone conditions. Some are dense enough to be consistent with rocky compositions. Some may be better targets for atmospheric characterization than older Kepler worlds because they are closer or orbit more favorable stars. The modern search is not looking for one famous planet to solve the question. It is building a list of targets, ranking them by what can actually be measured. LH 1140b, for example, has received attention because it is a dense planet in the habitable zone of a nearby red dwarf with a mass and radius suggesting a rocky or possibly water-rich nature, depending on interpretation. It transits, which opens the door to atmospheric study. Yet whether it has retained an atmosphere, whether it has surface water, and whether its climate is stable are all separate questions. A promising target is not a habitable world by declaration. It is a place where the next observation is worth making. The phrase Earth analog is one of the most demanding in astronomy. A true Earth analog would need to be roughly Earth-sized, rocky, in an Earth-like orbit around a Sun-like star, with an atmosphere and surface conditions that allow stable liquid water. Even then, geology and history would matter. So far, most known small temperate planets orbit red dwarfs because they are easier to detect. Sun-like stars are brighter and larger, making Earth-sized transits shallower, and Earth-year orbits slower to confirm. The planets most similar to Earth may be among the hardest to find with the methods that built the first catalogs. A super-Earth may sound inviting, but it is not necessarily a better Earth. Higher gravity changes atmosphere retention, mountain heights, volcanic behavior, and interior pressure. A larger rocky planet might maintain geological activity longer, but it might also develop a thick atmosphere or high-pressure conditions unlike Earth's. If it has too much water, continents may be absent. If it has too much gas, the surface may be unreachable under a deep envelope. Larger is not automatically more habitable. It is simply another set of physical constraints. Mini-Neptunes may be common, but their habitability is uncertain. A planet with a thick hydrogen-helium envelope could have no solid surface accessible under reasonable pressures. Some models allow temperate conditions at certain atmospheric depths or on ocean surfaces below hydrogen atmospheres, but these are not Earth-like environments. K2-18b sits in this broad category of uncertainty. The absence of a similar planet in our solar system makes these worlds hard to intuit. They are not scaled-up Earths or scaled-down Neptunes in any simple way. Hot Neptunes and warm sub-Neptunes can lose their atmospheres under stellar radiation. Some planets may be evaporating, leaving trails of gas. Others may have crossed the radius valley as their envelopes were stripped. These processes matter for habitability because a planet's atmosphere is often a leftover from a long struggle between gravity and radiation. A world that began with water and air may not keep either if its star and orbit take them away. Cold giant planets far from their stars are also part of the inventory. Direct imaging has revealed young massive worlds in wide orbits, still glowing with heat from formation. These planets are not life candidates in the usual sense, but they help scientists understand formation and migration. A giant planet far from its star may influence smaller inner planets by shaping debris disks, delivering comets, or destabilizing orbits. Habitability is sometimes affected by planets that are not themselves habitable. Moons around exoplanets remain difficult to confirm. Exomoons could be important because a large moon orbiting a giant planet in a habitable zone might hold an atmosphere or ocean. Tidal heating could warm interiors, but detecting moons requires subtle timing, duration changes, or direct signatures that are hard to separate from noise and planetary dynamics. The solar system contains many moons, and some are astrobiologically important. It would be surprising if other systems lacked them, but proving their existence around specific planets remains challenging. Rogue planets expand the search beyond starlight. If ejected planets are common, some may retain thick atmospheres or subsurface oceans warmed by internal heat. Without a star, surface photosynthesis would not operate in the familiar way, but geothermal or tidal energy in some circumstances could matter. Detection usually comes through microlensing or possibly infrared emission for young massive objects. These worlds would not have daylight. If they carry oceans, those oceans would be hidden under ice or atmosphere in interstellar darkness. White dwarf planets present another strange category. A white dwarf is the remnant core of a star like the Sun after it has exhausted nuclear fuel, shed outer layers, and collapsed into a dense Earth-sized object. Planets around white dwarfs may survive, migrate, or form from debris. Some could orbit in regions where temperatures allow liquid water for a time, though the evolution of the host star would be severe. A planet around a white dwarf would carry a history of stellar death. Habitability there, if possible, would be tied to survival after transformation. Pulsar planets show survival or formation under even harsher conditions. The first confirmed exoplanets orbited a pulsar where radiation and the aftermath of supernova evolution make conventional habitability unlikely. Yet their existence is scientifically important because it shows planets can appear in unexpected environments. The universe did not wait for astronomers to define comfortable categories before making planetary systems. Brown dwarfs sit between planets and stars, massive enough to glow with residual heat and in some cases burn deuterium, but not massive enough for sustained hydrogen fusion. They can host disks and perhaps planets. Free-floating planetary mass objects blur classification further. Are they planets if they do not orbit stars? Or should they be understood as low-mass brown dwarfs depending on formation history? Naming matters less than physics. What matters is mass, composition, formation, heat, and environment. The growing variety of known systems has made the search for life more disciplined, not less. It is tempting to imagine habitability everywhere because planets are common. But each class imposes constraints. A hot Jupiter is too hot and gaseous. A lava world is too irradiated. A mini Neptune may lack an accessible surface. A tidally locked red dwarf planet may depend on atmosphere survival. An ocean world may need rock-water exchange. The abundance of planets increases the number of possibilities. It does not remove the need to test each one. There may be worlds more habitable than Earth in some respects, sometimes called superhabitable in theoretical discussions. They might orbit stable stars somewhat cooler and longer-lived than the Sun, have larger land areas or shallower seas, or maintain stable climates over longer times. But these ideas are speculative because habitability is complex, and Earth is still the only example. It is possible that Earth is not optimal. It is also possible that the features that seem imperfect from one point of view are part of why life endured here. Even within Earth, habitability is uneven. Deserts, ice sheets, hydrothermal vents, deep crust, open ocean, acidic lakes, and high mountains all impose different limits. Life adapts locally. A planet's global habitability may depend on whether enough stable refuges exist through impacts, climate swings, stellar changes, and geological transitions. A distant telescope may only see the global average. Biology may live in the details below that average. This is one reason direct exploration of Mars remains relevant. Mars is not an exoplanet, and it is not an ocean moon, but it is a nearby world where habitability changed over time. Rovers have found sedimentary rocks, ancient river deltas, lakebed deposits, and minerals formed in water. Orbiters map ice, clays, and seasonal behavior. The search for ancient microbial life on Mars is a search for traces in rocks, not air. It teaches methods for reading a planet whose most habitable era may be long gone. Returned samples, meteorites, and laboratory simulations all feed into exoplanet thinking. Meteorites reveal early solar system chemistry. High-pressure experiments test interiors. Climate models explore atmospheres under different stars. Spectral databases help identify molecules. Biology experiments test survival under radiation, cold, salinity, acidity, and pressure. The study of alien worlds is not confined to telescopes. It also happens in clean rooms, vacuum chambers, spectrograph labs, and microscopes focused on materials from this system. The catalog of exoplanets is therefore a beginning map, not a finished atlas. Many entries are only radius, orbit, star, and a few derived quantities. Some have mass, fewer have atmospheric hints, fewer still are plausible life search targets. But the catalog is growing, and the questions are becoming sharper. 30 years ago, the number of confirmed planets around Sun-like stars was essentially zero. Now the difficulty is no longer believing planets exist, but understanding what they are. The most important systems may not yet be famous. They may be ordinary nearby stars, whose small planets are still hidden in noise. They may be discovered by future missions that monitor bright stars for long enough to catch Earth-like orbits. They may be found by radial velocity instruments that push precision lower, or by direct imaging telescopes designed specifically to separate faint planets from starlight. Somewhere in the data not yet collected, there may already be a planet whose atmosphere will become the first serious candidate for biology beyond Earth. Until then, the known systems serve as training grounds. TRAPPIST-1 teaches compact rocky architectures around red dwarfs. K218b teaches atmospheric ambiguity in sub-Neptunes. Hot Jupiters teach irradiated atmospheric physics. Kepler systems teach occurrence rates and orbital patterns. Directly imaged giants teach young planet formation. Europa and Enceladus teach hidden oceans. The search for life is assembled from all of them, not because all are habitable, but because each reveals part of how planets become what they are. The next stage of the search depends on instruments that do not yet feel as familiar as Kepler and TESS. Some are already working, some are being built. Some exist as designs, recommendations, prototypes, and engineering studies. Their goal is not simply to add more planets to the count, though they will do that. The deeper goal is characterization, to move from knowing that a planet exists to knowing what kind of atmosphere it has, what kind of star shapes it, and whether any part of it can be compared with the conditions that make Earth alive. Counting worlds was the first revolution. Reading them is the next. The James Webb Space Telescope is one of the central instruments of this era because it can gather infrared light with a large segmented mirror, cooled and stationed far from Earth's heat. Its spectrographs can measure molecules in exoplanet atmospheres, especially for large planets, and favorable small planets around small stars. Webb can also measure thermal emission from some rocky planets, helping determine whether they redistribute heat in ways consistent with atmospheres. But observing time is limited, targets are difficult, and many measurements require repeated transits. Webb is powerful enough to change the field, and still not powerful enough to answer every question. The Nancy Grace Roman Space Telescope will approach exoplanets partly through microlensing and direct imaging technology demonstration. Its wide-field survey will look toward dense star fields, where gravitational lensing events reveal planets at separations that transit surveys often miss. Roman's coronagraph will test high-contrast imaging technologies needed for future missions, even if its main direct imaging targets are not Earth twins. A technology demonstration can matter because future Earth imaging telescopes need more than a mirror. They need the ability to suppress starlight so deeply that a planet billions of times fainter can be separated from glare. ESA's Plato mission is designed to monitor bright stars and find terrestrial planets in orbits reaching toward habitable zones, especially around Sun-like stars. It will also study stellar oscillations, allowing scientists to characterize host stars more precisely. That matters because planet properties depend on star properties. A planet's radius, irradiation, and age are only as good as the star measurements beneath them. A better star makes a better planet. The point is simple, but it runs through all of exoplanet science. Ariel, another planned European mission, is aimed at surveying exoplanet atmospheres, especially warm and hot planets, to understand their chemical diversity and formation histories. It is not primarily a mission to find life. Its value lies in building atmospheric statistics, comparing compositions, clouds, and heat among many planets. Before life can be identified as exceptional, the ordinary range of lifeless atmospheres has to be understood. A biosignature search benefits from knowing what planets do when they are not alive. Ground-based extremely large telescopes will add another kind of power. Mirrors around 30 to 40 meters across can collect far more light than existing optical telescopes. Adaptive optics, high-resolution spectroscopy, and advanced instruments may help study exoplanet atmospheres, detect molecules, measure winds, and perhaps directly image certain nearby planets. The atmosphere of Earth remains both a problem and a resource. It blurs images, absorbs wavelengths, and emits light. But ground telescopes can be enormous and upgraded over time. A mountain observatory under a dark sky may become one of the places where the atmospheres of nearby worlds are first examined in detail. High-resolution spectroscopy can separate planetary signals by using Doppler shifts. As a planet orbits, the spectral lines from its atmosphere shift relative to the star and Earth's atmosphere. By searching for many molecular lines moving together at the expected velocity, astronomers can detect compounds even when the planet is not directly resolved as a disk. The method is powerful, but it requires precise models, strong instruments, and favorable targets. The signal is still small, and the star still dominates. Future concepts for a habitable worlds observatory or similar mission aim at the most difficult and important goal: directly imaging Earth-sized planets around nearby sun-like stars and taking spectra of their reflected light. Such a mission would need exquisite stability, starlight suppression, and careful target selection. It would likely observe only a limited number of nearby systems in enough detail to search for biosignatures. The first serious spectrum of an Earth-sized planet in the habitable zone of a sun-like star may require decades of preparation for a few photons gathered with extraordinary care. A starshade mission would approach the problem differently from an internal coronagraph. A large, precisely shaped screen would fly tens of thousands of kilometers from a telescope, blocking the star before its light enters the telescope and casting a deep shadow. The shape of the starshade petals would control diffraction. Aligning two spacecraft across such distances would be an engineering challenge, but the reward could be access to planets close to their stars in reflected light. The idea sounds almost delicate, a flower-shaped shadow in space, used not for beauty, but to reveal worlds hidden beside stars. No future telescope will remove the need for target prioritization. Nearby stars must be surveyed. Their planets must be found or constrained. Stellar activity must be measured. Dust in the system, called exozodiacal dust, can interfere with imaging by adding scattered light. Binary companions may complicate observations. The search for another Earth begins before the flagship telescope points. It begins with catalogs of stars, measurements of stellar quietness, radial velocity campaigns, and knowledge of which systems are worth the precious observing time. The Sun itself becomes a reference object in these preparations. Scientists study what Earth would look like from far away, as a pale dot, as a spectrum, as a rotating signal with clouds and continents, as a phase curve, as an atmosphere altered by seasons and life. Spacecraft images of Earth from distant viewpoints have been used to test retrieval methods. Earthshine observations, where sunlight reflected from Earth illuminates the dark part of the Moon, can provide disk-integrated spectra of our planet. To recognize another living world, it helps to know how poorly Earth can be seen when reduced to a point. Laboratories support this effort by measuring molecular absorption under different temperatures and pressures. Many molecules have spectral features that shift or broaden depending on environment. Clouds and aerosols must be modeled. Surface materials, minerals, ice, ocean, and vegetation like pigments all reflect light differently. Microorganisms can produce pigments that might create unusual spectral edges. A future spectrum will be only as useful as the libraries and models used to interpret it. The telescope gathers light, the laboratory helps translate it. Simulations are another instrument, though they do not observe the universe directly. Climate models test whether a tidally locked planet can distribute heat. Photochemical models test how gases change under different stellar ultraviolet spectra. Interior models estimate whether a planet can maintain volcanism or magnetic fields. Population models predict how planet formation produces the observed catalogs. A model is not evidence by itself. It is a tool that must be compared with evidence. Its value lies in making predictions that observations can challenge. Machine learning has entered the field because the data are large and subtle. Algorithms can search light curves for weak transit signals, classify false positives, analyze spectra, and identify patterns in surveys. But machine learning does not remove the need for physical understanding. A candidate found by an algorithm still has to be validated. A pattern still has to be interpreted. Automation can widen the search, but it cannot be allowed to turn uncertainty into certainty merely because the output looks precise. The future will also depend on long-term monitoring. Stellar cycles can last years. Planetary orbits can take years. Climate variations, if detectable, may require repeated observations. A biosignature candidate would need follow-up across instruments and methods. A single spectrum could start the conversation, but confidence would grow through recurrence, consistency, and independent checks. The most important discovery may not arrive in a single night. It may emerge over a decade, as one faint world refuses to fit lifeless explanations. Planetary protection and contamination control become more important for missions that sample material from ocean worlds or Mars. A spacecraft looking for organic molecules has to be built, cleaned, documented, and monitored so that Earth material does not become a false signal. Return samples require containment and careful handling. Searching for life is not only a question of sensitivity. It is also a question of cleanliness, chain of evidence, and trust in the sample. For Europa or Enceladus, a future lander or plume sampling mission could look for complex organics, isotopic patterns, cell-like structures, lipid-like membranes, chirality, and chemical gradients. It could compare molecules against non-biological chemistry and ask whether the distribution looks selected, maintained, or structured in ways life tends to produce. Even direct sampling would not make interpretation trivial. Life detection is not one instrument blinking yes. It is a suite of measurements building a case. For exoplanets, the equivalent suite may involve several telescopes. One mission finds the planet. Another measures mass. Another images it. Another takes spectra. Ground observations measure stellar activity. Models test climate. Laboratory data test molecules. The first inhabited exoplanet, if it is ever identified, may be a collaboration between instruments separated by continents, orbits, decades, and design philosophies. There is also a sociological side to evidence, though the script should not become about scientists as heroes. Large claims require independent teams. Data must be released, reprocessed, debated, and checked. Different models may disagree. The public may hear possibility as discovery, while researchers speak in probabilities. The search for life will test not only instruments, but the discipline of communication. A possible biosignature is not the same as a detected biosphere. This has already happened in smaller forms. Possible atmospheric detections around distant worlds are announced, revisited, weakened, strengthened, or reframed. A molecule appears in one analysis and becomes less certain in another. A planet once described as promising becomes less habitable when its density or stellar environment is better understood. This is not backtracking in the negative sense. It is science doing what it is supposed to do, replacing first impressions with better evidence. The future will probably bring many ambiguous worlds before it brings a clear one. There may be planets with oxygen but no methane, methane but no oxygen, water vapor but no surface ocean, carbon dioxide but uncertain pressure, clouds but hidden chemistry, or possible sulfur compounds that refuse to settle into one explanation. Ambiguity is not a detour, it is the landscape between ignorance and knowledge. The search also has to account for time in a stellar sense. Stars brighten as they age. Planetary climates respond. Red dwarfs change their activity levels. Flares and coronal mass ejections may erode atmospheres or drive chemistry. Massive stars live too briefly for long biological histories as we know them. K-dwarfs may offer stable, long-lived environments, which is one reason they are sometimes considered attractive targets. A habitable planet is tied to a star's life, not only its present light. Metallicity, the abundance of elements heavier than hydrogen and helium, can influence planet formation. Gas giants are more common around metal-rich stars, while small planets appear across a broad range. A star's composition can hint at the materials available in its birth disk, though the connection to planet composition is complicated. We cannot read a planet's geology directly from its star, but the star is part of the evidence because both formed from the same broader chemical environment. Galactic environment may matter too. Stars in dense clusters face more close encounters and radiation from massive neighbors. Regions with frequent supernovae could be harsher for atmospheres and life. The inner galaxy has more stars and heavy elements, but also more energetic events. The outer galaxy may be quieter, but less enriched. Habitability is not only a planetary question, it may be a galactic question, shaped by where and when a system formed in the Milky Way. Even so, the search remains anchored in individual measurements. A transit at a predicted time, a spectral line, a radial velocity curve, a plume particle, a radar reflection beneath ice, a temperature map, a light curve that repeats after 11 days or 37 days or 365. Large questions enter science through small records. The desire to know whether we are alone has to pass through pixels, photons, voltages, and calibrated errors. The best future instruments will not make the universe less mysterious by turning it into certainty. They will make the mystery more specific. Instead of asking whether there are planets, we will ask why a particular planet has carbon dioxide but little methane. Instead of asking whether ocean worlds exist, we will ask how ice and rock exchange material on a particular moon. Instead of asking whether red dwarf planets can be habitable, we will compare atmospheres in real systems. Progress does not always mean a final answer. Sometimes it means better questions aimed at real places. Earth is the control case, but it is not simple enough to be reduced to one lesson. From space, Earth looks obviously alive to instruments in some wavelengths and at some moments, but that appearance is the result of a long and uneven history. The planet formed more than 4.5 billion years ago from the same young solar system material as the other rocky planets. It endured impacts, differentiation, crust formation, atmospheric loss, volcanic outgassing, ocean formation, and bombardment by leftover bodies. Life did not begin on a finished planet. It began, if the evidence is read correctly, on a world still changing under heat, impacts, chemistry, and a young star. The earliest clear traces of life are ancient and debated in their details. Microfossils, isotopic ratios, stromatolites, and carbon signatures all contribute to the picture. But each line of evidence has to be interpreted carefully because rocks that old have often been altered. Still, life seems to have been present relatively early in Earth's history. That fact is encouraging, but it cannot be turned into a universal rule. One example does not tell us whether life begins easily whenever conditions allow, or whether Earth passed through a rare sequence of events that happened to work. The chemistry of life's origin may have required concentration, energy, surfaces, and cycles. Oceans are useful because they dissolve and move compounds, but a global ocean can also dilute molecules. Hydrothermal vents provide energy and mineral surfaces, but may disperse products. Wet-dry cycles near land can concentrate molecules, but require exposed surfaces. Ice can protect molecules and create concentrated brines. Ultraviolet light can damage molecules, but it can also drive useful reactions. The origin problem is not a single missing ingredient. It is a network of conditions that must produce self-sustaining chemistry before biology exists to maintain itself. Once life exists, evolution can explore environments that origin chemistry may not have favored. Microbes colonize hot springs, deep crust, sea ice, salt flats, acidic waters, alkaline vents, and high radiation sites. Some use sunlight. Others use chemical gradients. Some live with oxygen. Others are poisoned by it. Earth's biosphere is not one environment. It is a planetary collection of metabolisms, each tied to energy and matter in specific ways. This diversity matters for ocean worlds. If Enceladus has hydrothermal systems, microbial life as we know it would not need sunlight. If Europa exchanges oxidants from the surface with reductants from the ocean floor, chemical energy might be available. If Titan has complex organics and a subsurface ocean, prebiotic chemistry might occur in more than one reservoir, but every if hides a measurement. Ocean composition, energy flux, pH, salinity, rock contact, and stability all matter. A moon can have an ocean and still lack the right combination. On Earth, Plate tectonics may have played a major role in long-term habitability by recycling carbon, building continents, driving volcanism, and connecting surface and interior. Whether plate tectonics is necessary for life is unknown. Some planets may have stagnant lids, where the crust does not break into moving plates. They may still outgas, weather, and maintain climates in other ways, or they may not. Exoplanet geology is mostly invisible at present. Yet geology may decide whether a world remains habitable for billions of years. Magnetic fields are often discussed as protective shields, but their role is complicated. Earth's magnetic field helps deflect charged particles from the solar wind, reducing some atmospheric stripping and protecting the surface from certain radiation effects. Mars lost much of its global magnetic field early and later lost much of its atmosphere, though low gravity and solar wind also mattered. Venus lacks an Earth-like intrinsic magnetic field, but retains a thick atmosphere. A magnetic field can help, but it is not a simple requirement or guarantee. Atmosphere, gravity, stellar environment, and replenishment all interact. Life changed Earth most visibly through oxygenic photosynthesis. Cyanobacteria and their ancestors used sunlight to split water and release oxygen, but oxygen did not immediately fill the atmosphere. It reacted with iron, volcanic gases, and surface materials before accumulating. When it finally rose, it transformed chemistry, enabled ozone formation, and eventually allowed more energetic metabolisms. A gas that many modern organisms require was once a planetary pollutant to organisms adapted to an oxygen-poor world. Habitability depends on whom the planet is habitable for. From far away, an anoxic Earth might not look alive by modern biosignature standards. It might show methane under certain conditions, carbon dioxide, water vapor, and haze, but not abundant oxygen. Later Earth would look different. A future Earth, as the sun brightens, will eventually become less habitable, with changes to carbon dioxide, plant life, oceans, and climate long before the sun leaves the main sequence. A living planet has eras. A telescope sees only the era whose light reaches it. The history of mass extinctions is also relevant. Earth has suffered asteroid impacts, flood basalt eruptions, ocean anoxia, climate swings, and biological crises. Life persisted, but ecosystems changed profoundly. Complex life is more vulnerable than microbes. Intelligence, technology, and civilization are even more contingent. If the search is for life, microbial worlds may dominate. If the search is for intelligence, the probabilities may be very different. The two questions should not be merged without care. Earth's moon may have mattered by stabilizing axial tilt, driving tides, and shaping early environments, though the extent of its importance is debated. Jupiter may have influenced impact rates and delivery of volatiles, but not always protectively. The arrangement of the solar system affected Earth's history in ways that are hard to generalize. A planet is never only itself. It belongs to a system of companions, impacts, resonances, debris, and gravitational histories. The continents matter because they supply nutrients through weathering and erosion. Rivers carry phosphorus and other materials to the sea. Volcanism supplies gases. Hydrothermal systems exchange chemicals between rock and ocean. Burial and uplift recycle carbon. Without continents, an ocean planet might still have seafloor chemistry, but surface nutrient cycles could be different. A blue world with no land may be beautiful in an artist's rendering, but beauty does not tell us how its chemistry is renewed. Clouds are another complication. On Earth they cool by reflecting sunlight and warm by trapping infrared radiation, depending on height, thickness, and location. On tidally locked planets, clouds near the substellar point could reflect enough light to expand the inner edge of habitability in some models. On Venus, clouds reflect much sunlight, but the greenhouse atmosphere below is still extreme. Climate is an outcome of competing processes. A single feature rarely decides it alone. The carbonate-silicate cycle is often described as Earth's thermostat, but it works over long timescales. Rain dissolves carbon dioxide into weak acid, weathering rocks. Carbon reaches oceans, becomes carbonates, is buried, and eventually returns through volcanism. When the planet warms, weathering can increase, drawing down carbon dioxide. When it cools, weathering slows, allowing volcanic carbon dioxide to accumulate. This feedback depends on surface water, exposed rock, volcanism, and time. Whether exoplanets maintain similar cycles is one of the hidden questions behind the word habitable. Ocean chemistry may also control habitability. Salinity affects freezing, density, circulation, and biology. pH affects molecule stability and metabolism. Availability of phosphorus may limit life in some environments. Iron, sulfur, and other elements shape energy pathways. A planet can have an ocean and still be chemically starved, or chemically rich, or chemically hostile. The ocean's existence is the opening of a question, not its conclusion. For icy moons, the ice shell itself becomes an active boundary. If it is too thick and stagnant, ocean chemistry may be isolated from surface oxidants. If it convects, fractures, or erupts, exchange may occur. Plumes are valuable because they sample interior material, but not every ocean world has plumes, and not every plume reaches space. The accessibility of an ocean is not the same as the existence of an ocean. For science, accessibility may determine what can be known. The search for biosignatures in ice must consider radiation. On Europa, surface molecules are altered by Jupiter's radiation belts. Organic material near the surface may be destroyed or transformed unless buried or recently exposed. On Enceladus, radiation conditions differ, and plume particles may fall back onto the surface. Experiments suggest that some amino acids could survive at shallow depths under certain conditions. A future lander would need to know where to sample, not just what to sample. In atmospheres, radiation can create or destroy biosignature gases. Stellar ultraviolet light drives photochemistry. Flares can alter atmospheric escape and surface radiation. Ozone can shield, but only if oxygen exists to form it. Hydrogen-rich atmospheres can extend high above a planet, making spectral features stronger, but also changing chemistry and pressure. The same star that makes a planet visible by backlighting its atmosphere also changes that atmosphere. One of the most difficult questions is whether life tends to spread once it begins. On Earth, life became global. Microbes entered oceans, sediments, rocks, ice, atmosphere, and eventually land. But Earth has plate tectonics, water cycles, nutrients, and a climate that allowed expansion. A small habitat in an icy moon ocean might remain local if energy is limited. The difference between a living niche and a living planet may be enormous. Another question is whether life leaves unambiguous waste. Metabolism changes the environment by taking in energy-rich compounds and releasing products. On a planetary scale, enough life can alter atmospheric composition. But a small biosphere may be lost in background geochemistry. A deep ocean biosphere under ice may never affect the surface strongly. Detectability is not the same as existence. Astrobiology must always separate the two. The idea of panspermia, life, or prebiotic material moving between worlds, is sometimes raised because impacts can eject rocks from planets and moons. Martian meteorites have reached Earth. Organic molecules exist in comets and meteorites. Interstellar objects pass through planetary systems, but the survival of organisms across ejection, radiation, time and space, and impact is difficult, and evidence for life spreading between worlds remains absent. Panspermia could move life if life already exists somewhere, but it does not solve the origin question. It moves the question to another place. Interstellar objects like 1I Oumuamua and 2I/Borisov remind us that planetary systems exchange debris. These objects are not evidence of life, but they show that material can travel between stars. Their brief passages through the solar system gave astronomers rare samples of other systems' leftovers, observed from afar as moving points and spectra. A fragment from another planetary system can cross our neighborhood, but even then it remains mostly unknowable, passing too quickly for detailed study. Meteorites provide a nearer archive. Carbonaceous chondrites contain water-bearing minerals and organic compounds, showing that prebiotic chemistry is not confined to Earth. Amino acids can form through non-biological processes. This matters for biosignatures because organic molecules are not automatically signs of life. Organic chemistry is widespread. Biology is a special organization of chemistry, not merely the presence of carbon compounds. That distinction is central. A plume from Enceladus containing organics is exciting because it reveals chemical richness, but not because organics alone equal life. A spectrum with methane is exciting because methane participates in disequilibrium, not because methane alone equals life. An exoplanet in the habitable zone is exciting because liquid water is possible, not because habitability has been demonstrated. The search becomes trustworthy only when each step keeps its proper size. Still, the emotional force of the question remains. To find life elsewhere, even microbial life in an ocean under ice, would show that biology is not confined to one origin on one planet. To find a biosphere on an exoplanet would suggest that life can alter worlds across interstellar distances. To find independent life close to home would imply that the universe may be more fertile than the silence currently reveals. But the evidence has to arrive before the conclusion. Wanting the universe to be alive is not the same as measuring life. Earth's lesson is therefore double. It teaches what life can do to a planet, and it warns against assuming that all living planets must look like modern Earth. It provides gases to search for, and it shows how those gases changed over time. It provides ocean chemistry, and it shows that oceans alone were not the whole story. Earth is the only known answer, but it is not enough to define every possible answer. The search for life is often described as a search among planets, but planets are not scattered randomly through space. They orbit stars, and stars are born in galaxies, and galaxies evolve across cosmic time. A planet's possibility begins long before its surface cools. It begins in the chemical history of the gas cloud that forms its star. It depends on whether earlier generations of stars produced enough heavy elements, whether the young system was disturbed by nearby massive stars, whether the disk survived long enough to build planets, and whether later events allowed a climate to remain stable. A living world, if one is found, will be local and specific, but its ingredients will be cosmic. The Milky Way is more than a backdrop. It is a rotating disk of stars, gas, dust, dark matter, stellar remnants, nebulae, and molecular clouds. Star formation occurs in cold, dense regions where gravity can overcome pressure and turbulence. Massive stars live quickly and die violently, enriching the surrounding medium with heavy elements and radiation. Lower mass stars live much longer and provide stable light for immense stretches of time. The galaxy is an environment with neighborhoods. Not every region offers the same conditions for planet formation or long-term habitability. The Sun formed about 4.6 billion years ago from gas already enriched by earlier stars. Iron, silicon, oxygen, carbon, magnesium, and other elements in Earth were inherited from that prior history. Without supernovae and stellar winds, there would be no rocky planets as we know them. Without neutron star mergers and other heavy element sources, some rare elements would be scarce. The search for life, therefore, depends on stellar death as much as stellar birth. The material of biology was not created for biology. It was forged by astrophysical processes and later assembled into living systems on one planet. Metal-poor stars in the early universe may have had fewer materials for rocky planets, though small planets can form around a range of stellar compositions. Gas giants are more strongly correlated with metallicity, suggesting that heavy elements help build massive cores quickly. As galaxies age and become enriched, Planet formation changes. This does not mean life could not exist around older or metal-poor stars. It means that cosmic history affects the inventory of worlds available to the search. Star clusters can be difficult environments. In dense young clusters, close stellar encounters may disturb disks or planetary systems. Massive stars can bathe nearby disks in ultraviolet radiation, evaporating gas before giant planets form. Supernovae can inject short-lived radioactive isotopes and heavy elements, but also deliver destructive radiation if too close. A planetary system is born inside a community of stars, and that community may leave marks on what forms and what survives. At the same time, the Sun may have formed in a cluster and still produced a habitable Earth. Harsh environments do not automatically prevent planets. They change probabilities and histories. A nearby massive star might have contributed radioactive aluminum that heated planetesimals and affected water distribution. Encounters might have shaped outer reservoirs of comets. The same event can be helpful in one way and harmful in another. Planetary origin is rarely clean. The age of a star matters because life needs time, but time can also erode habitability. Massive stars burn quickly and die before complex biological evolution like Earth's could unfold. Sun-like stars provide billions of years, but slowly brighten, changing the habitable zone. Red dwarfs live extraordinarily long lives, but their early active phases may be severe. K-dwarfs, between sun-like stars and red dwarfs, may offer a balance of long lifetimes and more moderate activity, making them attractive in some habitability discussions. The best star for life is not known. It may depend on what kind of life and what kind of planet. A star's spectrum changes planetary climate and chemistry. Blue and ultraviolet light drive photochemistry and can damage molecules. Redder light from cool stars interacts differently with ice, clouds, and atmospheric gases. Photosynthesis around a red dwarf, if it existed, might use different pigment strategies from plants on Earth. Ice reflects visible light strongly, but absorbs more in near-infrared, which can alter climate feedbacks around cooler stars. Habitability is colored by starlight. The same planet under a different star would not be the same world. Stellar flares complicate the picture. A flare can increase ultraviolet and X-ray radiation dramatically for a short time. Repeated flaring can affect atmospheric chemistry, surface radiation, and atmospheric escape. But a thick atmosphere, ocean, ice cover, or subsurface habitat could provide shielding. Some flares may even supply energy for prebiotic chemistry. The question is not whether flares occur, but whether a planet's environment can absorb them without losing the conditions life needs. Planetary magnetic fields depend on interior structure, rotation, cooling, and conductive fluids. A magnetic field can help shape interactions with stellar wind, but it is not a complete shield. Venus, Mars, Earth, and the outer planet moons show that atmospheric survival and radiation exposure are controlled by multiple factors. When exoplanet habitability discussions mention magnetic protection, the honest answer is usually that it may matter and is hard to measure. Rotation rate affects climate. A rapidly rotating planet develops different wind patterns from a slow rotator. A tidally locked planet may develop a permanent day side, night side, and terminator region where temperatures are intermediate. Atmospheric thickness determines whether the night side collapses into frozen air or remains connected to the day side through circulation. Ocean currents can move heat differently from winds. Climate models of alien worlds are not decorative simulations. They are attempts to ask whether heat, water, and air can remain stable under unfamiliar conditions. Obliquity, the tilt of a planet's axis, affects seasons. A high obliquity planet may experience extreme seasonal changes, with poles receiving intense sunlight during part of the year. A low obliquity planet may have muted seasons. Chaotic obliquity variations could destabilize climate, though atmospheres and oceans might buffer changes. From a distance, seasons might be a signal. From the surface, they could be a challenge or a rhythm that life adapts to. Orbital eccentricity also matters. A planet with a highly elongated orbit receives very different amounts of light during its year. If the atmosphere and oceans store enough heat, the climate may remain tolerable. If not, the planet could swing between extremes. Eccentricity can also drive tidal heating, especially for moons and close-in planets. A number in an orbital catalog can represent climate stress, geological heat, or both. Moons can stabilize, heat, disturb, and illuminate. A large moon may affect tides and axial stability. Multiple moons around giant planets can enter resonances that produce tidal heating. Around exoplanets, moons remain mostly hypothetical because detections are uncertain, but the solar system shows their importance. The search for habitable environments cannot ignore satellites simply because they are hard to find. Asteroids and comets play double roles. They can deliver water and organics. They can also sterilize surfaces regionally or globally if impacts are large enough. Early bombardment may have shaped Earth's volatile inventory and created both destruction and opportunity. In mature systems, debris disks can signal remaining small body populations. Habitability is not the absence of impacts. It is survival through a history in which impacts occur at tolerable rates. Jupiter's role in Earth's history is often simplified as protector, but simulations show a more complicated picture. Giant planets can deflect some comets and send others inward. They can shape asteroid belts, deliver volatiles, excite eccentricities, and stabilize or destabilize smaller worlds. A system without giant planets may have different impact rates. A system with migrating giants may disrupt inner rocky planets. The architecture around a habitable planet may be as important as the planet's position. Planetary systems are not permanent in their first form. Stars lose mass as they evolve. Orbits can expand. Inner planets can be engulfed. Debris can be destabilized around white dwarfs. Planet-planet interactions can continue long after formation. Resonances can shift. A habitable world needs not only a habitable present, but a past that did not destroy it, and a future long enough for life to matter. The galaxy itself changes over billions of years. Star formation rates rise and fall. Spiral arms compress gas. Mergers disturb disks. Supernova rates vary. The Sun moves through the galaxy, crossing different regions over its orbit. These motions are slow on human timescales, but real on biological and geological timescales. Life on Earth has always traveled through the Milky Way, carried by a planet orbiting a star orbiting a galaxy, though no organism needed to know that for the motion to be true. Cosmic radiation adds another layer. High-energy particles from supernovae, active stars, and galactic sources can affect atmospheres and surfaces. Earth's atmosphere and magnetic environment provide shielding. Mars is more exposed. Europa's surface is dominated by Jupiter's radiation environment. Exoplanets may face very different particle conditions depending on their stars and locations. Radiation is not only danger, it is chemistry, mutation, atmospheric change, and an environmental variable that can both challenge and shape life. There is also the issue of observation through cosmic dust. Many young planetary systems are born in dusty regions that obscure visible light but glow in infrared. Infrared telescopes reveal protoplanetary disks, gaps, rings, and spirals that may indicate planet formation. ALMA, observing in millimeter wavelengths, has imaged disks with astonishing structure around young stars. Before a planet becomes a transit, it may first be hinted at by a gap in dust around an infant star. Those disk images have changed intuition about planet formation. Rings and gaps appear early, suggesting that planet formation may begin quickly. Dust traps may help grains grow despite drift toward the star. Spiral structures may indicate gravitational effects. Some features may be produced by planets, while others arise from disk physics alone. A gap in a disk is not automatically a planet, just as a dip in a light curve is not automatically a planet. The same scientific caution applies at every stage. Young planets are difficult to catch because they are embedded, hot, and still interacting with their disks. Some have been imaged as forming protoplanets, though claims can be debated. Accretion signatures, thermal emission, and disk structures help build the case. Seeing planet formation directly is rare, but every young disk is a reminder that the galaxy is still making worlds. Planet formation also shapes water delivery. Water may be incorporated as ice beyond the frost line, delivered inward by icy bodies, trapped in minerals, or lost during giant impacts. A planet's initial water budget can be altered by atmospheric escape, magma ocean phases, and later impacts. An ocean on an exoplanet is not only a climate feature, it is the end result of a supply chain that began in a disk of dust and gas. The origin of Earth's water remains studied through isotopes, meteorites, comets, and models of accretion. Some water may have been present in the building blocks of Earth, some may have arrived later. The ratio of deuterium to hydrogen helps compare sources, but the story is complex. If Earth's ocean has a complicated origin, oceans around other stars are unlikely to have a single simple pathway. A planet's interior can store water in minerals as well as on the surface. Mantle water affects melting, volcanism, plate tectonics, and long-term cycling. Super-Earth interiors may behave differently under higher pressures. Water-rich planets may have layers exotic to Earth. The ocean we see, or infer, may be only one reservoir in a planet's water inventory. Atmospheric escape creates another planetary filter. Light gases can escape thermally if molecules move fast enough, and non-thermal processes can remove ions and neutral atoms under stellar wind and radiation. Hydrodynamic escape can drag heavier atoms away during intense early irradiation. Observations of some close-in planets reveal escaping hydrogen and helium. A planet's sky can bleed into space. Over billions of years, that loss can determine whether the surface remains protected or exposed. Volcanism can rebuild an atmosphere by releasing gases from the interior. Impacts can both strip and deliver volatiles. Weathering can remove carbon dioxide. Biology, if present, can alter gases more profoundly. An atmosphere is not a one-time possession. It is a balance between sources and sinks. When astronomers model exoplanet habitability, they are often modeling a moving target with incomplete inputs. The mass may be uncertain. The atmosphere may be unknown. The star's history may be inferred, but not measured. The interior may be represented by simplified assumptions. The climate may have multiple stable states. This is not a weakness to hide. It is the honest state of trying to understand worlds we cannot visit. Even with these limits, patterns emerge. Small rocky planets are common. Planetary systems are diverse. Red dwarfs host many small worlds. Gas giants can migrate. Atmospheres can be measured for favorable targets. Ocean worlds exist in the solar system beyond the traditional surface habitable zone. The universe has not answered the life question, but it has removed the idea that Earth is surrounded by emptiness. The stars have planets, many of them. The search for alien worlds has also changed the meaning of silence. Before exoplanets were confirmed in large numbers, silence could be mixed with ignorance. Perhaps planets were rare. Perhaps the solar system was unusual. Perhaps there were few places to ask the question in the first place. That uncertainty has narrowed. Planets are not rare in the simple sense. Small planets exist. Temperate candidates exist. Organic chemistry exists in space. Water exists in many forms. The silence, if it remains, now sits against a richer background. It no longer says there are no worlds. It says that worlds alone do not immediately reveal whether they are inhabited. Radio searches entered the story before exoplanet catalogs were mature. A radio telescope can scan narrow frequency channels for signals that stand out from natural emission and human interference. Natural radio sources can be powerful and strange, but a very narrowband persistent signal from a fixed direction could be suspicious because known astrophysical processes usually spread energy across broader ranges or vary in characteristic ways. The difficulty is that Earth itself has become noisy. Satellites, aircraft, radar, phones, and electronics create interference that can imitate or obscure candidate signals. A possible detection has to be checked by other observatories at other times and against motion on the sky. Many candidates vanish under this scrutiny, not because the search is foolish, but because the standard must be high. Optical searches look for brief laser pulses or other concentrated light signals. Infrared searches imagine waste heat. Atmospheric searches consider industrial pollutants that would be hard to make in large quantities without technology. Some ideas are speculative, but they are grounded in a broader principle. Technology, like life, might alter its environment in detectable ways. Still, the leap from detectable biosphere to detectable civilization is large. A planet could be alive for billions of years with no radio transmitters. A technological species could choose not to broadcast, use communication methods that do not leak, or exist during a window too short for us to overlap with it. The search for intelligence is not simply the search for planets plus time. It requires assumptions about behavior, longevity, and detectability that remain largely unknown. The Fermi question asks why, if life or intelligence is common, we do not see obvious evidence. But the question contains many possible answers. Interstellar travel may be difficult enough to remain rare. Civilizations may be short-lived or quiet. They may not expand. They may use technologies we do not recognize. The galaxy may contain life mostly at microbial levels. Intelligent life may be separated by vast distances and mismatched times. Signals may weaken, spread, or be absorbed into noise. Catastrophes may interrupt technological phases. Or life may be genuinely rare. None of these possibilities is proven. The silence is not one answer. It is a set of constraints placed on many answers. A galaxy can be old and still not synchronized. The Milky Way is more than 13 billion years old, but stars and planets formed at different times. A civilization that rose 1 million years ago and vanished after 10,000 years would be ancient from a human perspective and almost invisible from a galactic one. A signal sent deliberately toward Earth before humans built radio telescopes might have passed unnoticed. A biosphere on a planet 500 light-years away is seen as it was 500 years ago, not as it is now. The search is complicated by time as well as distance. We are not surveying a single present moment across the galaxy. We are receiving a layered past, arriving at light speed from every direction. This time delay affects even the simplest image of a planet. The transit of a world around a star 100 light-years away is an event from 100 years ago. The atmospheric spectrum belongs to that older state. If a planet changed, if a flare stripped part of its atmosphere, if a biosphere collapsed or began after that light left, the telescope would not yet know. Astronomy is always historical. To look outward is to accept that the universe reaches us after the fact. For biosignatures, this is not usually a problem, because geological and biological changes often occur slowly, but catastrophic events, stellar flares, impacts, and technological signals can occur on shorter timescales. A planet might look habitable while entering an unstable era. Another might appear lifeless in the ancient light we receive, but have become active since then. This is not a reason to abandon the search. It is a reminder that every observation is a sample from time. A planet's truth is not frozen, but our evidence arrives in slices. The scale of the Milky Way also means that even optimistic probabilities can feel sparse. If life exists on 1 in 1,000 habitable planets, that may still mean many living worlds across the galaxy, but the nearest one could be far away. If technological civilizations last only briefly, their overlap with us may be unlikely even if many have existed. If microbial life is common, but intelligence rare, telescopes may find atmospheric biosignatures long before radio signals. Different versions of the question produce different searches. Are we looking for life? Complex life? Intelligence? Technology? Or communication? They are not the same. It is possible that the first evidence of life beyond Earth will not be dramatic to the eye. It may be a table in a paper, a spectrum with error bars, a set of models showing that abiotic explanations are weak, and years of follow-up narrowing the uncertainties. It may not come with an image of a blue planet. It may not even be universally accepted at first. The most important discovery may begin as something small enough to fit inside a graph. This would not make it less profound. The confirmation of exoplanets began with wobbles and timing signals, not photographs of mountains. The discovery of cosmic expansion began with galaxy spectra and redshifts. The cosmic microwave background was first a persistent microwave signal that had to be understood. Gravitational waves arrived as tiny distortions in kilometer-long detectors. Science often meets the enormous through the slight. The search for life may do the same, not because life is slight, but because distance makes even a planet's atmosphere faint. There is a temptation to imagine that a living exoplanet would settle old human questions immediately. It would not. If a biosignature were confirmed, scientists would then ask what kind of life could produce it, how old the biosphere is, whether it is microbial, whether it has continents and oceans, whether oxygen is present, whether climate is stable, whether the planet has moons, whether the signal changes with seasons, whether the atmosphere shows industry or only biology. One answer opens the next set of unknowns. Discovery is not the end of mystery. It is the beginning of more precise mystery. If life were found on Europa or Enceladus, the questions would be different but equally deep. Is it related to Earth life through exchanged material, or does it represent a second origin? Does it use Na or Arna, or a different information system? Does it share amino acid chirality with terrestrial life? Does it live only in a narrow chemical zone, or throughout the ocean? Did it begin there or arrive there? Does it have a long evolutionary history under ice? Direct sampling might answer some of these questions and complicate others. A living cell under a microscope would be extraordinary, but its meaning would depend on chemistry, ancestry, and environment. The strongest result would be independent life, a second genesis. That would imply that life can begin more than once in one planetary system if conditions allow, and it would transform estimates for the galaxy. But establishing independence would be difficult. Similar biochemistry might mean shared ancestry, or it might mean chemistry has preferred solutions. Different biochemistry might strongly suggest independence, but even then the evidence would need care. The word life itself may have to be applied through measurable properties: metabolism, replication, evolution, compartmentalization, information, and chemical organization. Life as we know it is cellular, carbon-based, water-using, and built on genetic polymers. Speculation about other chemistries is interesting, but the search usually begins with water and carbon because they are known to work and because carbon chemistry is richly versatile. Silicon-based life, ammonia solvents, or methane lakes are discussed, especially in relation to Titan-like environments, but they remain speculative compared with water-based biology. Starting with Earth-like chemistry is not a failure of imagination. It is an evidence-based starting point, yet even Earth-based imagination has range. Life might exist in briny channels within ice. It might cling to mineral surfaces in dark oceans. It might float in temperate layers of an atmosphere, though sustaining such an ecosystem would be difficult. It might live beneath rock, using chemical energy from radiolysis or water rock reactions. It might be sparse enough that a lander could miss it. The first search may fail not because life is absent everywhere, but because life is small, local, or hidden. This is one reason scientists are careful with landing sites and sampling strategies. On Mars, ancient lakebeds and deltas are attractive because they preserve sediments where biosignatures could be trapped. On Europa, relatively young surface material, regions connected to the interior, and radiation exposure all matter. On Enceladus, plume sampling depends on trajectory, particle speed, and instrument sensitivity. Life detection is a problem in geography as much as chemistry. The right world is not enough if the wrong place is sampled. For exoplanets, the sampling problem becomes global because the telescope cannot choose a rock or shoreline. It sees the planet as a whole, or as a thin atmospheric limb, or as reflected light averaged across hemispheres. This averaging can help if a biosphere is global, but it can hide regional details. Earth's disk integrated light contains clouds, oceans, deserts, forests, ice, and atmosphere, all blended together. Another planet's blended light may be even harder to separate, because its surface, if visible at all, will be unknown. Some researchers study Earth as if it were an exoplanet by taking observations from spacecraft at a distance or by averaging data into unresolved spectra. These studies ask what a distant observer could know: rotation period, cloud cover, oceans, continents, vegetation, atmospheric gases, seasons. They reveal both promise and humility. Earth is detectable as unusual under certain conditions, but not every feature is obvious all the time. Even our own planet becomes mysterious when reduced to 1 pixel. The search for life is therefore a search through limits. Instrument limits, model limits, biological limits, geological limits, time limits. But limits are not walls, they are measurements of what must be improved. Kepler had limits and still changed astronomy. TESS has limits and still supplies targets. Webb has limits and still opens atmospheres. Europa Clipper will have limits and still reveal whether Europa's ocean world is more or less habitable than current evidence suggests. Each instrument narrows the darkness without pretending to remove it completely. There is a quiet continuity between the first exoplanet detections and the search now underway. A star wobbled. A star dimmed. A spectrum changed. A spacecraft tasted ice grains in a plume. A rover drilled sediment. A telescope measured infrared light from a small planet's dayside. These are different observations, but they share a method: infer the unseen from the effect it has on something measurable. The universe is not silent because it lacks information. It is silent because information must be translated. The translation takes time, and it takes restraint. A channel about space mystery can dwell in uncertainty, but the uncertainty should not be inflated beyond the evidence. The real universe is strange enough without making it supernatural. Planets do not need to be haunted to be compelling. A small rocky world crossing a red dwarf, an ocean under a moon's ice, a gas in a spectrum that might have more than one origin, a star whose flares complicate habitability. These are physical mysteries. They are made of matter, radiation, chemistry, and time. There is another reason the search remains difficult. Life may be both common and hard to notice. A planet covered in microbial mats could change its atmosphere slowly. A subsurface biosphere might barely touch the sky. A biosphere under a thick haze might leave signals that overlap with ordinary photochemistry. Even on Earth, life is obvious to a person walking through a forest or standing beside the ocean, but from interstellar distance, those forests and oceans are compressed into light. The planet becomes an average. Continents rotate in and out of view. Clouds cover evidence. Ice advances and retreats. Seasons alter color and gas. To read such a planet, scientists have to separate biology from weather, geology, and viewing angle. The reverse possibility is just as challenging. A lifeless planet can sometimes look alive in one narrow measurement. A dry world that lost oceans can keep oxygen. A volcanic world can release gases that resemble metabolic products. A planet around an active star can have photochemistry unlike Earth's. A hydrogen-rich atmosphere can produce molecules in ways that would be rare here. This is why astrobiologists often speak of environmental context. Temperature, pressure, stellar spectrum, geological activity, atmospheric escape, and planetary mass all become part of the life question. Without context, a molecule is only a molecule. There is no shame in this slowness. The first maps of Earth were incomplete and sometimes wrong, even though their makers lived on the same planet. The first maps of Mars were shaped by telescope limits and imagination. The first interpretation of Venus as a tropical world collapsed when radar and spacecraft revealed the real surface conditions. Again and again, better instruments replaced attractive assumptions. Exoplanets demand the same discipline under far harder conditions. A good search for alien life must be willing to give up a beautiful idea when the data points somewhere else. A living planet may not resemble the images used to represent it. Artist concepts are useful because they give the mind something to hold, but they are not observations. A blue surface in an illustration may stand for water suggested by a model, not a photographed ocean. Clouds may be painted because clouds are plausible, not because a telescope resolved them. Continents may be added for scale and familiarity. In the actual data, there may only be a spectrum, a transit depth, a mass estimate, and a range of possible atmospheres. The image helps communicate the possibility, but the graph carries the evidence. This distinction matters because alien worlds are easy to overimagine. A planet in the habitable zone is quickly turned into a shoreline. A possible ocean becomes waves. A possible molecule becomes biology. A distant red dwarf system becomes a place of sunsets and climates before the atmosphere is even known. Imagination has a place, but it has to follow measurement rather than outrun it. The most interesting planet in a catalog is not always the one with the most dramatic artist rendering. It is often the one whose measurements can be improved. Scientific uncertainty is not a blank space where any story can be placed. It is a measured range of possibilities. For one planet, the radius may be known well, but the mass poorly. For another, the orbit may be secure, but the atmosphere unconstrained. For another, the star may be active enough that atmospheric features are ambiguous. The uncertainty has structure, and that structure guides the next observation. A good model does not simply say perhaps. It says which perhaps is consistent with the data, and which perhaps is not. When scientists choose a target, they are choosing a compromise. A nearby planet may not transit. A transiting planet may orbit an active star. A quiet sun-like star may be too large for small transit signals. A planet with a strong atmospheric spectrum may be too hot for life. A temperate rocky world may require dozens of transits to build enough signal. Observing time on major telescopes is precious, and every hour spent on one target is an hour not spent on another. The search is therefore practical as well as philosophical. It advances through decisions about signal to noise, stellar brightness, orbital period, and whether a question is answerable now. The same practicality governs mission design. A spacecraft sent to Europa cannot carry every possible instrument. A telescope cannot observe every wavelength with equal power. A survey mission trades depth for breadth, while a flagship observatory trades breadth for detail. Engineers manage mass, power, thermal stability, pointing accuracy, data rates, and risk. Scientists choose measurement priorities. Every discovery is shaped by hardware before it becomes shaped by interpretation. Even so, the search has a cumulative power. One mission finds candidates. Another characterizes stars. Another studies atmospheres. Another tests technology. A laboratory experiment measures how molecules survive radiation in ice. A climate model predicts where clouds form on a tidally locked planet. A planetary mission maps the chemistry of an icy moon. These pieces may seem separate, but together they reduce the number of ways the universe can hide. The search for life is not one telescope staring into the dark. It is an ecosystem of evidence. The emotional center of the search remains simple. Somewhere beyond Earth, There may be a world where water persists, energy flows, chemistry cycles, and molecules have organized into systems that copy and evolve. That possibility is powerful because it is not magic. It is matter behaving under laws that also operate here. It would not make Earth ordinary in a careless sense. It would place Earth inside a wider category of living worlds, showing that biology is not an isolated event in the history of one planet. But until the evidence arrives, the possibility remains exactly that: possible, not settled. This balance between possibility and restraint is what gives the search its real atmosphere. The unknown is not empty darkness. It is a set of worlds with measured orbits, estimated densities, spectral hints, and physical histories. Some are already ruled out for familiar life. Some remain open. Some are so poorly known that even their category is uncertain. The work now is to move them, one by one, from rumor to measurement, from measurement to context, and from context, perhaps someday, to a sign that cannot be explained without life. Imagine the next promising planet entering a catalog not as a painting, but as a row of values: stellar radius, orbital period, transit depth, estimated equilibrium temperature, planet radius, candidate disposition, follow-up priority. At first, there is no ocean in the data, no sky, no surface, no horizon. There is only a star and a repeating loss of light. Then, another instrument measures the star's motion and adds mass. Another observation checks nearby sources. Another telescope records a spectrum during transit. The row becomes a system. The system becomes a world that can be discussed with increasing precision. The transformation is slow, but it is the only honest way a planet so far away can become real to us. A future archive may contain dozens of such targets. Some will disappoint. A planet thought to be rocky may turn out to be wrapped in gas. A world in the habitable zone may have no atmosphere. A possible water feature may become a cloud problem or a stellar contamination problem. A candidate biosignature may fade under better data. This will not mean the search has failed. It will mean the search is learning which planets are only attractive from a distance and which ones remain interesting when the evidence improves. The history of exoplanets has already shown that the universe can be more varied than expectation. It can also be less cooperative than hope. The strongest candidates will be those that survive this process. A rocky planet with a measured atmosphere. A temperature range consistent with liquid water. A star quiet enough to interpret. A spectrum showing gases that are difficult to maintain without active sources. A climate model that does not collapse into obvious impossibility. Repeated observations from independent instruments. A lack of convincing abiotic explanations. Even then, the language may remain cautious, evidence consistent with biology, a possible biosignature, a high-priority target for follow-up. The first living exoplanet, if it is recognized from afar, may arrive not with certainty all at once, but with resistance to every simpler explanation. There is patience in this kind of science, but it is not passive. It is the patience of engineers aligning mirrors, of observers waiting for a transit that lasts only a few hours, of software teams removing detector artifacts, of chemists measuring spectra in laboratories, of modelers testing atmospheres under starlight, unlike the sun's, of mission planners choosing one target when hundreds deserve attention. Each step is small compared with the question, but the question cannot be reached except through small steps. The galaxy is too large for shortcuts. A claim that life exists beyond Earth would have to cross the full distance between desire and evidence. The ocean worlds nearby may provide a different path. Europa Clipper will map, measure, and listen with radar and fields and spectra. It will fly past Europa again and again, building a picture from repeated close encounters. A future Enceladus mission could pass through plumes with instruments designed specifically for life detection, measuring complex organics, salts, isotopes, and possible patterns of selection. A Titan mission can explore organic chemistry in an atmosphere and surface environment unlike any place on Earth. These missions do not replace exoplanet astronomy. They give it nearby laboratories where the physics and chemistry of habitability can be tested with more direct evidence. If one of these moons is sterile, that result will matter. It will show that water, rock, and energy can coexist without producing life, at least in that environment. If more than one is sterile, the constraints grow. If one is alive, the meaning would be enormous. But even a sterile ocean world is not a failure. It teaches what habitability lacks when biology does not appear. The search for life needs negative results as much as positive ones, because the universe cannot be understood only through the worlds that excite us most. A lifeless ocean may be one of the most important comparisons biology ever receives. For exoplanets, the negative results will also matter. A survey of small planets around red dwarfs might reveal that many have lost atmospheres. That would reshape expectations. A survey of sub-Neptunes might show that Hycean conditions are rare or common. A future direct imaging mission might find that Earth-sized planets around Sun-like stars often have clouds, or dry surfaces, or thick carbon dioxide atmospheres, or no atmospheres at all. The answer to whether life is common may come through population statistics before it comes through one spectacular world. The search may also reveal categories that are not yet named well. The history of exoplanets has repeatedly done this. Hot Jupiters forced migration into the conversation. Super-Earths and sub-Neptunes became central despite being absent from the solar system. Compact resonance systems showed architectures unlike ours. Ocean worlds under ice expanded habitability beyond surface sunlight. Future observations may reveal atmospheric classes, climate states, or planetary histories that current language handles poorly. Science often begins with old words stretched over new evidence, then slowly invents better ones. There is an observational humility in the fact that most exoplanets will never be known in detail. The catalog may grow to tens of thousands, then hundreds of thousands, while only a fraction receive atmospheric study. A smaller fraction will be plausible life search targets. The galaxy may contain billions of planets, but human attention and instrument time are finite. The search will always be selective. We will not know every world. We will learn from the ones aligned, bright, nearby, quiet, large, small, lucky, or strange enough to reveal themselves. Yet a small sample can still change everything. The first confirmed exoplanets changed the status of planetary systems from expectation to evidence. The first atmospheric spectra of hot Jupiters changed exoplanets from points in orbital diagrams into physical worlds with chemistry and weather. The first detailed studies of super-Earths and sub-Neptunes changed ideas about what kinds of planets are common. The first strong biosignature candidate, even before final confirmation, would change the direction of astronomy, planetary science, biology, and philosophy, because it would focus the question on a real place rather than an abstract possibility. The viewer may imagine alien life as something that looks back, but the first evidence may not look back at all. It may be microbes below ice, chemistry in a plume, oxygen and methane in a spectrum, or a planet whose atmosphere refuses to settle into equilibrium. It may be life with no eyes, no signals, no technology, no awareness that there is a galaxy above it. That would still be enough. The discovery that life has begun twice, or that a distant atmosphere bears the mark of biology, would mean that Earth is not the only place where matter learned to maintain itself, copy itself, and evolve. No responsible search can promise when that will happen. It may be soon by scientific standards, or it may take generations. It may happen in a solar system sample before it happens in an exoplanet spectrum. It may happen first as a debated claim that becomes stronger with time. Or It may not happen at all within the reach of current methods, forcing future instruments to become more capable and future theories more precise. The uncertainty is not empty. It gives shape to the work that remains. The night sky still looks much the way it did before exoplanets were known. Stars scattered across darkness, the Milky Way pale under clear skies, planets of our own system moving slowly among constellations. The difference is hidden inside what we now know those stars can carry. Around many of them, worlds move. Some are scorched. Some are frozen. Some are wrapped in hydrogen. Some may be bare rock. Some may hold oceans under ice or air. Some may have lost their water before they could use it. Some may be waiting in data not yet gathered, crossing their stars in shadows too small for older instruments to notice. The search for life does not make Earth less important. It makes Earth more informative. Our planet is the example against which instruments, models, and claims are tested. Its atmosphere shows what a biosphere can do. Its ancient rocks show that life can be difficult to read even nearby. Its neighboring planets show how similar beginnings can diverge. Its ocean moons show that water can hide far from sunlight. The more alien worlds are found, the more specific Earth's lessons become. A telescope mirror cools in space and turns toward a faint star. A spectrograph waits for a transit. A spacecraft on its way to Jupiter carries instruments that will read ice and fields and dust. A radio dish sweeps a quiet band of sky. In a data archive, old light curves are searched again with new tools. None of these scenes is dramatic by itself. Together they are how a species confined to one planet begins to test whether life is confined there too. The scale is enormous, but the work is exact. The final answer is not in the catalogs yet. There is no confirmed second biosphere, no verified alien ocean full of organisms, no atmosphere beyond Earth accepted as living. What exists is evidence of planets in abundance, evidence of water in many places, evidence of ocean worlds close enough to study, evidence that atmospheres can be measured across light years, and evidence that the next questions are no longer unreachable. The unknown has become structured. It has names, targets, instruments, and observing programs. Somewhere, a small planet may be crossing a star right now from our point of view, dimming it by a fraction so slight that only a detector will notice. The light from that event may already be moving toward a telescope. It may carry nothing more than the signature of a bare rock. It may carry the trace of an atmosphere. It may carry the first weak clue of a world with water and active chemistry. We do not know yet. The signal has to arrive, and then it has to survive the careful work of being understood. For now, the search continues in the most physical way possible. Mirrors collecting photons, spacecraft crossing dark distances, spectra marked by missing wavelengths, computers folding light curves, and scientists refusing to call mystery an answer before the evidence is ready. Beyond the sun, the planets are real. Some are oceans, some are deserts, some are giants, some are shadows against stars, and among them, somewhere in the measured dark, may be a world where chemistry has crossed the same threshold it crossed here, turning a planet from a place with water into a place with life.